Something growls, invisible, unstoppable, ancient. This is Cygnus X-1, a black hole that should not exist. Born from a star too massive to leave anything behind, yet here it is, devouring light itself, wrapped in mystery like a cosmic predator hiding in plain sight. In 1964, it flickered on our instruments. By 1971, astronomers were stunned. This was no ordinary X-ray source. It orbited a giant blue star, pulling matter like a vampire. Its mass? Far beyond what any theory predicted. Cygnus X-1 is a remarkable cosmic object that has captivated astronomers since its discovery in 1964. Located approximately 6,000 light-years away in the constellation Cygnus, it is one of the strongest X-ray sources visible from Earth. This celestial powerhouse is actually a binary system, consisting of a blue supergiant star and an incredibly dense companion. The companion object in Cygnus X-1 is what truly sets it apart. Scientists have concluded that it is a stellar mass black hole, one of the first such objects to be identified. This black hole, with a mass roughly 15 times that of our Sun, is locked in a cosmic dance with its stellar partner. As it pulls material from the blue supergiant, this matter forms a swirling disk around the black hole, heating up to extreme temperatures and emitting powerful X-rays. Cygnus X-1 has played a crucial role in our understanding of black holes and the extreme physics that govern them. Its study has provided valuable insights into how these enigmatic objects interact with their surroundings and how they affect the evolution of massive stars. The system continues to be a focal point for research, helping scientists refine theories about the nature of gravity and the behavior of matter in extreme conditions. The existence of Cygnus X-1 sparked intense debate among astronomers when it was first discovered. Its properties were so extreme that some scientists, including Stephen Hawking, initially bet against it being a black hole. However, as evidence mounted, even the skeptics were convinced, marking a turning point in our acceptance and understanding of these cosmic phenomena. Cygnus X-1 was first discovered in 1964 during a rocket flight. Astronomers detected a powerful source of X-rays in the constellation Cygnus, which they initially couldn't explain. This mysterious object, later named Cygnus X-1, became the subject of intense study and debate in the scientific community. At the time of its discovery, scientists were unsure about the nature of this X-ray source. It wasn't until the early 1970s that researchers began to seriously consider the possibility that Cygnus X-1 might be a black hole. This hypothesis was controversial, as black holes were still largely theoretical at that point. The discovery of Cygnus X-1 marked a significant milestone in astrophysics. It provided scientists with the first strong observational evidence for the existence of black holes, which had been predicted by Einstein's theory of general relativity decades earlier. This finding opened up new avenues for research and deepened our understanding of the most extreme objects in the universe. Over the years, continued observations and advancements in technology have allowed astronomers to study Cygnus X-1 in greater detail, confirming its status as a black hole and revealing more about its properties and behavior. The story of Cygnus X-1 demonstrates how scientific discoveries often lead to new questions and push the boundaries of our knowledge about the cosmos. The initial discovery of Cygnus X-1 was made by a team of researchers led by Riccardo Giacconi in 1962. Using instruments aboard a suborbital rocket, they detected a strong X-ray source in the constellation Cygnus. This groundbreaking observation marked the birth of X-ray astronomy and opened up a new window for studying the universe. At the time of its discovery, the nature of Cygnus X-1 remained a mystery. Scientists knew it was an incredibly bright source of X-rays, but they could not determine what kind of cosmic object could produce such intense radiation. It was not until years later that researchers began to suspect Cygnus X-1 might be something extraordinary, a black hole. The discovery of Cygnus X-1 sparked intense debate and research in the astronomical community. As more data was gathered and analyzed, scientists gradually pieced together the puzzle of this enigmatic object. The story of Cygnus X-1 highlights how scientific discoveries often unfold over time, with initial observations leading to years of follow-up studies and theoretical work. Today, Cygnus X-1 is recognized as one of the most well-studied black holes in our galaxy, but its journey from an unknown X-ray source to a confirmed black hole spans decades of scientific inquiry and technological advancement. Cygnus X-1 holds a special place in astrophysics as the first cosmic object widely accepted as a black hole. Discovered in 1964 during a rocket flight, this celestial body initially puzzled scientists with its intense X-ray emissions. These emissions were far too powerful to originate from a normal star, leading researchers to consider more exotic explanations. The breakthrough came when astronomers realized Cygnus X-1 was part of a binary system. They observed a massive blue supergiant star orbiting an invisible companion. This unseen object, despite being only about 15 times the mass of our Sun, exerted a gravitational pull strong enough to strip matter from its stellar partner. The intense X-rays were produced as this stolen material spiraled into the mysterious dark body. This discovery provided compelling evidence for the existence of black holes, which until then had been purely theoretical constructs. Cygnus X-1 matched the predictions for a stellar mass black hole so closely that it forced the scientific community to seriously consider these extreme objects as real phenomena. Even skeptics like Stephen Hawking, who had bet against the existence of black holes, eventually conceded in the face of mounting evidence from Cygnus X-1. The study of Cygnus X-1 has continued to yield valuable insights into the nature of black holes and the extreme physics governing their behavior. It has become a crucial laboratory for testing theories of gravity, accretion processes, and high-energy astrophysics, cementing its status as a landmark object in our understanding of the universe. Cygnus X-1 earned its name through a combination of its location and the nature of its discovery. The first part, Cygnus, refers to the constellation in which this cosmic object resides. Cygnus is Latin for swan, and the constellation itself resembles a swan flying across the night sky. The second part of the name, X-1, reveals its significance in the field of X-ray astronomy. It was the first X-ray source detected in the constellation Cygnus, hence the designation X-1. This powerful X-ray emitter was discovered in 1964 during a rocket flight carrying X-ray detectors. At the time of its discovery, the true nature of Cygnus X-1 remained a mystery. Scientists knew it was an incredibly bright X-ray source, but they couldn't determine what type of object could produce such intense radiation. It wasn't until later observations and studies that Cygnus X-1 was identified as a strong candidate for a black hole. The naming convention used for Cygnus X-1 is common in X-ray astronomy. Other X-ray sources in the same constellation would be named Cygnus X-2, Cygnus X-3, and so on. This system helps astronomers catalog and refer to these powerful cosmic X-ray emitters across different regions of the sky. Cygnus X-1 stands out as a remarkable celestial object, primarily because it was the first strong candidate for a black hole ever discovered. Located in the constellation Cygnus, this cosmic powerhouse is a binary system consisting of a blue supergiant star and an incredibly dense companion object. What truly sets Cygnus X-1 apart is the nature of this companion. Its immense gravitational pull causes it to strip away material from its stellar partner, creating a swirling disk of superheated gas around itself. As this material falls inward, it emits powerful X-rays, making Cygnus X-1 one of the brightest X-ray sources in our galaxy. The companion object in Cygnus X-1 is estimated to have a mass about 15 times that of our Sun, yet it is compressed into a space smaller than a city on Earth. This extreme density, combined with its ability to trap even light within its gravitational field, provides compelling evidence that we are observing a stellar mass black hole. Cygnus X-1 continues to be a focal point for astronomers and astrophysicists, offering valuable insights into the behavior of matter and energy in the most extreme conditions in the universe. Its discovery and ongoing study have significantly advanced our understanding of black holes and the fundamental laws of physics. Cygnus X-1 challenges our understanding of stellar evolution and black hole formation. This cosmic oddity is a binary system containing a blue supergiant star and what scientists believe to be a black hole. The black hole in Cygnus X-1 is unusually massive, weighing in at about 21 times the mass of our Sun. This extraordinary heft poses a problem for conventional theories of stellar collapse and black hole formation. According to our current models, stars of this size should typically end their lives as neutron stars, not black holes. The presence of such a massive black hole in Cygnus X-1 suggests that either our understanding of stellar evolution is incomplete, or that this system formed through an unusual process we have yet to fully comprehend. Furthermore, the black hole in Cygnus X-1 appears to be spinning at nearly the maximum rate allowed by Einstein's theory of general relativity. This extreme rotation adds another layer of complexity to the system, as it is difficult to explain how the black hole achieved such a rapid spin during its formation or subsequent evolution. These peculiarities make Cygnus X-1 a cosmic conundrum, challenging astronomers to rethink their theories and driving further research into the life cycles of massive stars and the formation of black holes. The system's existence pushes the boundaries of our knowledge, highlighting the vast mysteries that still exist in our universe. The discovery of Cygnus X-1 in 1964 sparked intense debate and excitement within the scientific community. Astronomers were initially puzzled by this powerful source of X-rays in the constellation Cygnus. The object's unusual properties challenged existing theories and pushed the boundaries of astrophysics. Many scientists were skeptical about the true nature of Cygnus X-1. Some proposed it might be a neutron star, while others suggested it could be the first observed black hole. This uncertainty led to a flurry of research and observations as astronomers worldwide sought to unravel the mystery. The possibility that Cygnus X-1 might be a black hole was particularly controversial. At the time, black holes were purely theoretical constructs predicted by Einstein's general theory of relativity but never observed. The idea that scientists might have found evidence of an actual black hole was both thrilling and unsettling. As more data accumulated, the scientific community gradually shifted towards accepting Cygnus X-1 as a strong black hole candidate. This realization marked a significant milestone in astrophysics, providing the first observational evidence for these enigmatic objects and opening up new avenues for research into the most extreme phenomena in our universe. The Cygnus constellation is a prominent feature of the Northern Hemisphere's night sky. It can be found soaring high overhead during summer evenings and early autumn nights. Cygnus, also known as the Swan, is easily recognizable due to its distinctive cross-like shape, which has earned it the nickname the Northern Cross. This celestial swan flies along the plane of the Milky Way, making it a rich area for stargazing. It is surrounded by other well-known constellations, with Lyra to its west, Draco to its north, Cepheus to its northeast, and Pegasus to its southeast. The brightest star in Cygnus, Deneb, forms part of the famous Summer Triangle asterism, along with Vega in Lyra and Altair in Aquila. For observers in mid-northern latitudes, Cygnus is circumpolar, meaning it never sets below the horizon. This makes it visible throughout the year, though it is most prominent during summer and early fall. In these seasons, the constellation appears directly overhead around midnight. To locate Cygnus, start by finding the Summer Triangle. Once you've identified this large, bright triangle in the sky, look for the star at the northernmost point. That's Deneb, marking the tail of the swan. From there, trace the long neck down to Albireo at the beak, forming the vertical bar of the Northern Cross. The outstretched wings form the horizontal bar, completing this celestial avian figure that has captured the imagination of stargazers for millennia. The Cygnus constellation, also known as the Swan, has captivated stargazers for millennia. In Greek mythology, this celestial swan is often associated with the story of Zeus and his many romantic pursuits. According to legend, Zeus transformed himself into a beautiful swan to seduce Leda, the queen of Sparta. This tale of divine trickery and mortal enchantment became immortalized in the night sky. Another mythological interpretation links Cygnus to Orpheus, the legendary musician of ancient Greece. After his death, Orpheus was said to have been transformed into a swan and placed among the stars. This connection between the constellation and music has inspired countless poets and artists throughout history. In other cultures, the Cygnus constellation takes on different meanings. Native American tribes often saw it as a bird flying along the Milky Way, which they considered the path of souls to the afterlife. Chinese astronomers viewed this star pattern as a celestial bridge spanning the Milky Way, connecting two star-crossed lovers who could meet only once a year. These diverse myths and legends surrounding Cygnus demonstrate how ancient cultures sought to explain the mysteries of the night sky through storytelling. The enduring appeal of these tales continues to spark imagination and wonder, even in our modern era of scientific understanding. Cygnus X-1 is a remarkable cosmic object located within the boundaries of the Cygnus constellation. This celestial powerhouse is a binary system consisting of a blue supergiant star and a black hole locked in a gravitational dance. The Cygnus constellation, also known as the Swan, provides the backdrop for this extraordinary pairing, with Cygnus X-1 situated near the Swan's left wing. Discovered in 1964 during a rocket flight, Cygnus X-1 was one of the first cosmic X-ray sources ever detected. Its intense X-ray emissions, which give it the X in its name, are produced as matter from the blue supergiant is pulled into the black hole's immense gravitational field. This process creates a swirling disk of superheated material around the black hole, generating powerful X-rays that can be observed from Earth. The presence of Cygnus X-1 adds a layer of scientific intrigue to the already mythologically rich Cygnus constellation. While ancient cultures saw a swan flying across the Milky Way in this star pattern, modern astronomers see it as a cosmic laboratory for studying extreme physics. The black hole in Cygnus X-1 is estimated to be about 14.5 times the mass of our Sun, making it one of the most massive stellar black holes known in our galaxy. Cygnus X-1's location within the Cygnus constellation has made it a target of intense study for astronomers. Its relative proximity to Earth, at about 6,000 light-years away, allows for detailed observations that have significantly advanced our understanding of black holes, accretion processes, and high-energy astrophysics. This cosmic wonder continues to captivate scientists and stargazers alike, bridging ancient stellar patterns with cutting-edge astrophysical research. The Cygnus constellation is home to several fascinating celestial objects that captivate astronomers and stargazers alike. One of the most prominent features is the North America Nebula, an expansive cloud of ionized hydrogen gas that stretches across 40 light-years. Its distinctive shape resembles the continent of North America, making it a popular target for astrophotography. Another remarkable object in Cygnus is the Veil Nebula, a sprawling supernova remnant. This delicate structure of glowing filaments is the result of a massive star that exploded about 8,000 years ago. The nebula continues to expand, driven by the energy of that ancient cosmic cataclysm. Cygnus also harbors the intriguing Cygnus X-1, one of the strongest X-ray sources in the sky. This binary system consists of a blue supergiant star orbiting what is believed to be a black hole. The intense gravitational pull of the black hole draws material from its companion star, creating a swirling accretion disk that emits powerful X-rays. The constellation is also home to Deneb, one of the brightest stars visible in the night sky. This blue-white supergiant is one of the most luminous known stars, shining with the power of over 50,000 suns. Despite its great distance from Earth, Deneb's immense brightness makes it a prominent feature of the Summer Triangle asterism. The Cygnus constellation is not a single point in space, but rather a collection of stars spread across a vast area of the night sky. These stars are at different distances from Earth, making it challenging to give a single, definitive answer to how far away the constellation is. The stars that make up Cygnus range from relatively close to incredibly distant. Deneb, one of the brightest stars in Cygnus and part of the Summer Triangle, is approximately 2,000 light-years away from Earth. This means that the light we see from Deneb today left the star about 2,000 years ago. In contrast, Albireo, another prominent star in Cygnus, is much closer at roughly 400 light-years from Earth. Other stars in the constellation can be even farther, with some potentially lying thousands of light-years beyond Deneb. It's important to note that these distances are based on our current best measurements and may be refined as our astronomical techniques improve. The vast range of distances within Cygnus serves as a reminder of the immense scale of our galaxy and the challenges in mapping the cosmos. The Cygnus constellation holds a special place in astronomy for several reasons. Known as the Swan, this celestial pattern graces our night sky with its distinctive cross shape, often called the Northern Cross. Cygnus is home to some of the brightest and most studied stars in our galaxy, including Deneb, one of the most luminous stars visible to the naked eye. Astronomers find Cygnus particularly intriguing due to its position along the Milky Way. This location makes it a rich hunting ground for various cosmic phenomena. The constellation contains numerous nebulae, star-forming regions, and stellar remnants, providing a wealth of targets for both professional and amateur astronomers. One of the most notable features in Cygnus is the Cygnus Loop, also known as the Veil Nebula. This expansive supernova remnant offers valuable insights into the life cycles of massive stars and the processes that shape our galaxy. The constellation also harbors Cygnus X-1, the first discovered black hole candidate, which continues to be a subject of intense study in astrophysics. Furthermore, Cygnus plays a crucial role in our understanding of stellar evolution. The diversity of stars within this constellation, ranging from newborn to ancient, allows astronomers to observe and analyze different stages of stellar life. This makes Cygnus an invaluable cosmic laboratory, contributing significantly to our knowledge of the universe and its workings. Locating Cygnus X-1 within the constellation, Cygnus requires patience and careful observation. Amateur astronomers can start by identifying the prominent Northern Cross asterism, which forms the main body of Cygnus the Swan. The bright star at the top of the cross is Deneb, marking the swan's tail. From Deneb, trace a line down to Albireo, the star at the base of the cross, representing the swan's beak. Cygnus X-1 itself is not visible to the naked eye, as it is a black hole. However, its binary companion, a blue supergiant star, can be observed with a moderate-sized telescope. This star is located near the left wing of the Swan, about 2/3 of the way from Albireo to Eta Cygni, a star marking the left wing tip. To pinpoint the location more precisely, look for a triangle formed by the stars Eta Cygni, Zeta Cygni, and Delta Cygni. Cygnus X-1's companion star lies just inside this triangle, closer to the Eta-Zeta side. While the black hole itself remains invisible, observing its companion provides a unique opportunity to study the effects of one of the most extreme objects in our galaxy. For the best viewing experience, choose a clear night with minimal light pollution and allow your eyes to adjust to the darkness. Using star charts or astronomy apps can greatly assist in navigating the constellation and locating this fascinating cosmic system. Black holes are among the most enigmatic objects in the universe. They are regions of space where gravity is so intense that nothing, not even light, can escape their pull. This extreme gravitational force is created when a massive star collapses at the end of its life, compressing an enormous amount of matter into an incredibly small space. At the heart of a black hole lies what scientists call the singularity, a point of infinite density where the laws of physics as we know them break down. Surrounding this is the event horizon, often described as the black hole's boundary. Once anything crosses this threshold, it can never return to the outside universe. Despite their name, black holes are not entirely black. They can emit a faint glow known as Hawking radiation, named after the renowned physicist Stephen Hawking. This radiation is thought to cause black holes to slowly evaporate over incredibly long periods of time, although this process has not yet been directly observed. Black holes come in different sizes, from stellar mass black holes formed from collapsed stars to supermassive black holes that lurk at the centers of galaxies, including our own Milky Way. These cosmic behemoths continue to fascinate scientists and push the boundaries of our understanding of the universe. Black holes form when massive stars reach the end of their lives in a spectacular explosion called a supernova. As the star collapses under its own gravity, its core becomes incredibly dense. If the star is massive enough, typically at least 20 times the mass of our Sun, the gravitational force becomes so intense that nothing can escape its pull, not even light. The boundary beyond which nothing can escape is called the event horizon. Inside this boundary, the laws of physics as we know them break down. The material from the collapsed star continues to be crushed into an infinitely small point called a singularity, where density and gravity become infinite. Not all black holes form from dying stars. Supermassive black holes found at the centers of galaxies, including our own Milky Way, are thought to form through different processes. These giants, millions or billions of times more massive than stellar black holes, might grow by merging with other black holes or by consuming vast amounts of gas and dust over billions of years. Scientists have also proposed the existence of primordial black holes, which may have formed in the extreme conditions of the early universe, just moments after the Big Bang. While their existence remains theoretical, these ancient black holes could provide insights into the formation of the universe itself. Black holes come in a range of sizes, each with unique characteristics. Stellar black holes form when massive stars collapse at the end of their lives. These cosmic objects typically have masses between 5 and several dozen times that of our Sun. Supermassive black holes, on the other hand, are true giants of the cosmos. They reside at the centers of most galaxies, including our own Milky Way, and can contain millions or even billions of solar masses. Between these two extremes lie intermediate mass black holes. These elusive objects are thought to have masses ranging from about 100 to 100,000 times that of the Sun. While their existence has long been theorized, confirming observations have proven challenging. At the smallest end of the spectrum are miniature black holes. Some theories suggest these could have formed in the extreme conditions of the early universe. If they exist, they might be as small as a single atom, yet possess the mass of a large mountain. Their diminutive size would make them extraordinarily difficult to detect. Rotating black holes, also known as Kerr black holes, add another layer of complexity. These spin rapidly, dragging the fabric of space-time around them in a process called frame dragging. This rotation can have profound effects on nearby matter and energy, potentially even creating conditions for extracting energy from the black hole itself. The event horizon is a crucial feature of black holes, marking the boundary beyond which nothing can escape their immense gravitational pull. This invisible border separates the observable universe from the black hole's interior, where the laws of physics as we know them break down. Once any object, including light itself, crosses the event horizon, it becomes forever trapped within the black hole's grasp. At the event horizon, the escape velocity equals the speed of light. This means that even the fastest moving particles in the universe cannot overcome the black hole's gravitational force once they pass this point. The size of the event horizon depends on the mass of the black hole, with more massive black holes having larger event horizons. For an outside observer, time appears to slow down for objects approaching the event horizon due to the extreme gravitational effects. This phenomenon, known as gravitational time dilation, becomes more pronounced closer to the event horizon. As a result, an object falling into a black hole would appear to freeze in time from an external perspective, never quite reaching the event horizon itself. The event horizon represents one of the most mysterious and intriguing aspects of black holes. It challenges our understanding of space, time, and the fundamental nature of the universe, making it a focal point for ongoing research in astrophysics and theoretical physics. As objects approach the event horizon of a black hole, they experience extreme gravitational forces. Once they cross this boundary, their fate is sealed. Matter that passes the event horizon is inexorably pulled toward the center of the black hole, a point of incredible density known as the singularity. This journey is a one-way trip, as nothing, not even light, can escape once it has crossed the event horizon. Light behaves differently from matter, but meets a similar end. Photons, the particles that make up light, are bent and twisted by the intense gravity near the event horizon. Those that cross this threshold are trapped forever, spiraling inward toward the singularity. This is why black holes appear black to outside observers. No light can escape to reach our eyes. The extreme conditions beyond the event horizon cause matter to be stretched and compressed in a process called spaghettification. As it falls deeper into the black hole, the differences in gravitational force between the top and bottom of an object become so great that it is literally torn apart. Even fundamental particles are eventually broken down as they approach the singularity. Time itself behaves strangely near and beyond the event horizon. From the perspective of an outside observer, time appears to slow down for objects approaching the black hole, eventually seeming to stop altogether at the event horizon. However, for the falling object, time would appear to pass normally, highlighting the relative nature of time in extreme gravitational fields. Black holes may be invisible, but scientists have developed ingenious methods to detect these cosmic enigmas. One key approach involves observing the effects black holes have on nearby objects and space itself. As matter falls towards a black hole, it forms a swirling disk of gas and dust called an accretion disk. This material heats up to extreme temperatures, emitting powerful X-rays that can be detected by space-based telescopes. Another telltale sign of a black hole is its gravitational influence on surrounding stars. By carefully tracking the motions of stars near the center of our galaxy, astronomers have discovered a supermassive black hole lurking at the heart of the Milky Way. The erratic orbits and high velocities of these stars reveal the presence of an incredibly massive, yet invisible, object. Gravitational waves, ripples in the fabric of space-time predicted by Einstein, offer yet another way to detect black holes. When two black holes collide and merge, they send out gravitational waves that can be measured by highly sensitive instruments on Earth. These waves provide valuable information about the mass and spin of the black holes involved in the cosmic collision. Recently, scientists captured the first ever image of a black hole using a global network of radio telescopes. This groundbreaking achievement allowed us to see the shadow cast by the event horizon, the point of no return beyond which nothing can escape the black hole's gravitational pull. While black holes themselves remain invisible, these diverse detection methods continue to unveil their secrets and expand our understanding of these fascinating cosmic objects. Hawking radiation is a remarkable phenomenon predicted by the renowned physicist Stephen Hawking. This theoretical form of radiation is thought to be emitted by black holes, challenging our understanding of these cosmic enigmas. According to Hawking's groundbreaking work, the intense gravitational field of a black hole causes quantum fluctuations near its event horizon. These fluctuations result in the creation of particle-antiparticle pairs. Occasionally, one particle of the pair falls into the black hole while the other escapes, appearing to an outside observer as radiation emanating from the black hole itself. This process leads to a gradual decrease in the mass and energy of the black hole over time. For large black holes, this effect is extremely slow, but for smaller ones, it could lead to eventual evaporation. The smaller the black hole, the faster it radiates and shrinks. Hawking radiation connects the worlds of quantum mechanics and general relativity, two fundamental theories that have long resisted unification. While it remains undetected due to its extremely faint nature, this concept has profound implications for our understanding of black holes and the ultimate fate of the universe. Black holes are cosmic phenomena that warp the very fabric of space-time in extreme ways. These incredibly dense objects exert such powerful gravitational forces that they distort the space and time around them, creating what scientists call a gravitational well. Imagine space-time as a stretched rubber sheet. A black hole would be like an immensely heavy bowling ball placed on this sheet, causing a deep depression that curves the surrounding area. This warping of space-time has profound effects on anything that ventures near a black hole. As objects approach, they experience time dilation, where time appears to slow down from an outside observer's perspective. This effect becomes more pronounced the closer an object gets to the black hole's event horizon, the boundary beyond which nothing can escape its gravitational pull. The extreme curvature of space-time near a black hole also affects the path of light. Light rays that pass close to a black hole can be bent or even trapped in orbit around it, creating what astronomers call a photon sphere. This bending of light can result in gravitational lensing, where the black hole acts like a cosmic magnifying glass, distorting and amplifying the light from distant objects behind it. Perhaps most intriguingly, the intense gravitational field of a black hole is thought to create singularities, points where the laws of physics as we understand them break down. These singularities represent the ultimate warping of space-time, where our current models of the universe reach their limits, and new physics may be required to explain what happens at the heart of a black hole. At the heart of a black hole lies one of the most perplexing phenomena in the universe, the singularity. This is a point where our current understanding of physics breaks down, and the laws that govern space and time as we know them cease to function. The singularity is believed to be infinitely dense, containing all the mass of the black hole compressed into a single point of zero volume. This extreme concentration of matter creates a gravitational pull so intense that nothing, not even light, can escape once it passes the black hole's event horizon. What makes the singularity particularly mysterious is that it represents a boundary in our mathematical models. The equations we use to describe gravity and space-time produce infinite values at the singularity, suggesting that our current theories are incomplete. Some scientists speculate that new physics, possibly involving quantum gravity, might be needed to fully understand what happens at this extreme point. The concept of a singularity challenges our notions of reality and pushes the limits of our scientific knowledge. It remains one of the most intriguing and least understood aspects of black holes, driving ongoing research in theoretical physics and cosmology. Cygnus X-1, one of the most famous black holes in our galaxy, has been the subject of intense study for decades. Astronomers estimate its mass to be approximately 15 times that of our Sun. This substantial mass, combined with its relatively small size, confirms its nature as a stellar mass black hole. The mass of Cygnus X-1 has been determined through careful observations of its interactions with its companion star. This binary system allows scientists to use the laws of orbital mechanics to calculate the black hole's mass with impressive accuracy. The companion star, a blue supergiant, orbits the black hole every 5.5 days, providing regular opportunities for measurement and analysis. Interestingly, the mass of Cygnus X-1 places it at the upper end of the mass range for stellar mass black holes. This makes it an invaluable object of study, as it helps astronomers understand the processes of stellar evolution and the formation of black holes. The substantial mass of Cygnus X-1 suggests that it formed from the collapse of a particularly massive star, shedding light on the life cycles of the universe's most enormous stellar objects. Cygnus X-1 stands out as a remarkable black hole in our cosmic neighborhood. Located about 6,000 light-years from Earth, this stellar mass black hole is approximately 15 times more massive than our Sun. While this might sound enormous, Cygnus X-1 is actually relatively small compared to many other known black holes in the universe. Supermassive black holes, which reside at the centers of galaxies, dwarf Cygnus X-1 in comparison. These behemoths can have masses millions or even billions of times greater than our Sun. The black hole at the center of our Milky Way galaxy, Sagittarius A star, is about 4 million times more massive than the Sun, making it over 260,000 times more massive than Cygnus X-1. However, when compared to other stellar mass black holes, Cygnus X-1 is quite large. Many black holes formed from collapsed stars have masses between 5 and 10 times that of our Sun. Cygnus X-1, pushing 15 solar masses, places it at the upper end of the stellar mass black hole range. Intermediate mass black holes bridge the gap between stellar mass and supermassive black holes. These elusive objects, with masses ranging from hundreds to hundreds of thousands of solar masses, are still rarely observed. Cygnus X-1, while impressive, is dwarfed by these intermediate giants, further illustrating the vast scale of black holes in our universe. Cygnus X-1 is a remarkable cosmic object, a black hole that spins at an astonishing rate. This stellar remnant rotates on its axis at nearly half the speed of light. To put this into perspective, its equator is spinning at about 150 million meters per second. This extreme rotation is a result of the black hole's formation process and the conservation of angular momentum from its progenitor star. The rapid spin of Cygnus X-1 has significant implications for its surrounding environment. It creates a powerful gravitational effect known as frame dragging, where the fabric of space-time itself is twisted and dragged along with the black hole's rotation. This phenomenon intensifies the already extreme conditions near the black hole, affecting the behavior of nearby matter and energy. Scientists determine the rotation speed of black holes like Cygnus X-1 through careful observations of X-ray emissions from the accretion disk, the swirling matter falling into the black hole. The specific patterns and intensities of these emissions provide crucial data about the black hole's properties, including its spin rate. The incredible rotation of Cygnus X-1 serves as a cosmic laboratory, allowing researchers to study the effects of extreme gravity and test the predictions of general relativity in ways impossible to replicate on Earth. Its rapid spin continues to fascinate astronomers and push the boundaries of our understanding of the universe's most enigmatic objects. Cygnus X-1, a stellar mass black hole in our galaxy, spins at an astonishing rate, completing nearly 1,000 rotations per second. This rapid rotation has profound effects on the space around it. As the black hole spins, it drags the fabric of space-time along with it, a phenomenon known as frame dragging. This warping of space-time creates a swirling vortex around the black hole, influencing the motion of nearby objects and light. The intense rotation also amplifies the black hole's magnetic field, which interacts with the surrounding accretion disk. This interaction generates powerful jets of particles that shoot out from the poles of the black hole at nearly the speed of light. These jets extend for thousands of light-years, influencing the interstellar medium far beyond the immediate vicinity of Cygnus X-1. Furthermore, the rotation affects the structure of the accretion disk itself. The innermost stable circular orbit, The closest point at which matter can safely orbit the black hole is pulled closer to the event horizon due to the spin. This allows matter to get closer to the black hole before falling in, increasing the efficiency of energy extraction from the infalling material. The effects of Cygnus X-1's rotation extend even further, influencing gravitational waves emitted during events like black hole mergers. The spin of the black hole alters the pattern of these waves, providing astronomers with valuable information about the nature of these extreme cosmic objects and the space-time around them. Frame dragging is a fascinating phenomenon predicted by Einstein's theory of general relativity. It occurs when a massive, rotating object, like a black hole or a neutron star, twists the fabric of space-time around it. This effect is similar to how a spinning ball in a pool of water would drag the surrounding liquid, creating a vortex. In the case of frame dragging, the rotating object pulls space and time along with it, affecting the motion of nearby objects and even light itself. Cygnus X-1, a well-known binary star system, provides an excellent opportunity to observe frame dragging in action. This system consists of a blue supergiant star orbiting a black hole, which is continuously pulling matter from its companion. As the black hole spins rapidly, it drags the space-time around it, creating a swirling effect that influences the accretion disk of material surrounding it. The frame dragging effect in Cygnus X-1 causes the inner part of the accretion disk to rotate faster than it would if the black hole were not spinning. This additional rotation alters the X-ray emissions from the system, allowing scientists to measure the black hole's spin rate. By studying these emissions, researchers have determined that the black hole in Cygnus X-1 is rotating at nearly the maximum rate allowed by general relativity. This remarkable example of frame dragging in Cygnus X-1 not only confirms Einstein's predictions, but also provides valuable insights into the behavior of matter and energy in extreme gravitational environments. It showcases how the rotation of massive objects can have profound effects on the very fabric of space-time, demonstrating the intricate dance between matter, gravity, and the structure of our universe. Cygnus X-1, one of the most famous black holes in our galaxy, is estimated to be quite young in cosmic terms. Astronomers believe this celestial object is approximately 6 million years old. This age puts Cygnus X-1 in its stellar infancy compared to many other cosmic structures in our universe. The age of Cygnus X-1 has been determined through careful analysis of its companion star and the surrounding stellar environment. Scientists have studied the properties of the massive blue supergiant star orbiting the black hole, as well as the characteristics of the nearby star-forming regions. This relatively youthful age helps explain the intense activity observed around Cygnus X-1. The black hole is still actively feeding on material from its companion star, producing powerful X-ray emissions and relativistic jets. These energetic phenomena make Cygnus X-1 a valuable subject for studying the early stages of black hole evolution and their impact on surrounding space. Understanding the age of objects like Cygnus X-1 provides crucial insights into the life cycles of massive stars and the formation of stellar mass black holes. It allows scientists to piece together the cosmic timeline of our galaxy and better comprehend the processes that shape our universe. Cygnus X-1 is a well-known binary star system located approximately 6,000 light-years from Earth. It consists of a blue supergiant star orbiting alongside a black hole. The accretion disk around Cygnus X-1 is a swirling collection of gas and dust that surrounds this black hole. As material from the blue supergiant star is pulled towards the black hole by its immense gravitational force, it doesn't fall directly in. Instead, it forms a flat, rotating disk around the black hole. This disk is heated to extremely high temperatures due to friction and compression, causing it to emit powerful X-rays that we can detect from Earth. The accretion disk of Cygnus X-1 is a prime example of how matter behaves in the presence of intense gravitational fields. It serves as a natural laboratory for studying the physics of black holes and the extreme conditions found in their vicinity. Scientists use observations of this accretion disk to test theories about general relativity and the behavior of matter in strong gravitational fields. The study of accretion disks, like the one around Cygnus X-1, has significantly advanced our understanding of black holes and the processes that occur around them. These disks play a crucial role in the growth and evolution of black holes, as well as in the emission of energy that makes these otherwise invisible objects detectable to our instruments. Cygnus X-1, one of the most famous black holes in our galaxy, reveals much of its nature through its accretion disk. This swirling collection of superheated gas and dust plays a crucial role in our ability to study and understand this otherwise invisible cosmic object. The accretion disk acts as a cosmic spotlight, illuminating the black hole's presence and properties. As matter in the disk spirals towards the black hole, it heats up to extreme temperatures, emitting intense X-rays and other forms of radiation. These emissions provide astronomers with valuable data about the black hole's mass, spin, and overall behavior. The disk's radiation also allows us to measure the black hole's spin rate. As the inner edge of the accretion disk orbits close to the event horizon, it experiences intense gravitational effects. By analyzing the energy spectrum of the X-rays emitted from this region, scientists can determine how fast the black hole is rotating. Furthermore, the accretion disk's behavior helps confirm predictions of general relativity. The way light and matter interact near the black hole's event horizon provides a natural laboratory for testing Einstein's theories under extreme conditions, furthering our understanding of fundamental physics and the nature of spacetime itself. Cygnus X-1's companion star is a blue supergiant known as HDE 226868. This massive star is about 40 times the mass of our Sun and has a surface temperature of around 30,000 Kelvin, making it one of the hottest and most luminous stars known. The blue supergiant orbits the black hole at the heart of Cygnus X-1, completing one orbit approximately every 5.5 days. This close orbital dance causes the star to be slowly stripped of its outer layers, which are then pulled into the black hole's accretion disk. As material from the blue supergiant falls towards the black hole, it heats up to extreme temperatures and emits powerful X-rays. These X-rays are what initially led to the discovery of Cygnus X-1, making it one of the first suspected black holes ever identified. The relationship between Cygnus X-1 and its companion star offers astronomers a unique opportunity to study the interactions between black holes and massive stars, providing valuable insights into the life cycles of these cosmic giants and the extreme physics at play in such systems. The interaction between a companion star and a black hole is a cosmic dance of extraordinary proportions. As the two objects orbit each other, the immense gravitational pull of the black hole begins to strip away the outer layers of the companion star. This process, known as accretion, sees stellar material spiraling towards the black hole in a swirling disk of superheated gas and dust. As this material approaches the black hole, it accelerates to incredible speeds, reaching temperatures of millions of degrees. The friction and compression in the accretion disk cause the material to emit intense radiation across the electromagnetic spectrum, from radio waves to X-rays. This emission can make the binary system incredibly bright, often outshining entire galaxies. The black hole does not consume all the material from its companion. Some of it is violently ejected in the form of powerful jets that shoot out perpendicular to the accretion disk. These jets can extend for thousands of light years, influencing the surrounding space and potentially triggering star formation in distant regions. Over time, the continuous loss of material can dramatically alter the companion star. It may become a smaller, denser object, or in extreme cases, be completely consumed by the black hole. This interaction showcases the profound influence black holes can exert on their cosmic neighbors, shaping the evolution of stars and the dynamics of galaxies. The orbital period of this binary star system is approximately 78 years. This means that it takes nearly 8 decades for the two stars to complete one full revolution around their common center of mass. This lengthy orbital dance is a testament to the vast distances and powerful gravitational forces at play in this cosmic pair. Binary star systems are quite common in our galaxy, with some estimates suggesting that over half of all stars exist in multiple star configurations. The orbital periods of these systems can vary dramatically, from mere hours in the case of very close binaries to thousands of years for widely separated pairs. In this particular system, the 78-year orbit indicates that the stars are at a moderate distance from each other. This separation allows astronomers to study both stars individually, providing valuable insights into stellar evolution, mass transfer, and the complex gravitational interactions that govern binary systems. Observations of this binary pair over multiple orbits have allowed scientists to precisely calculate their masses, sizes, and evolutionary states. This wealth of data contributes to our broader understanding of stellar physics and the life cycles of stars throughout the universe. Cygnus X-1's binary nature fundamentally shapes its behavior and characteristics. This system consists of a massive blue supergiant star orbiting in close proximity to a black hole. The intense gravitational pull of the black hole strips away the outer layers of the supergiant, creating a steady stream of matter flowing from the star towards its dark companion. This transfer of material forms an accretion disk around the black hole, a swirling vortex of superheated gas and dust. As matter in the disk spirals inward, it reaches extreme temperatures and emits powerful X-rays, making Cygnus X-1 one of the brightest X-ray sources in our galaxy. The interaction between the two objects also produces jets of particles that shoot out from the system at nearly the speed of light. The orbital dance of these two celestial bodies creates periodic variations in the X-ray emissions we observe. As the supergiant moves in its orbit, it periodically blocks our view of the accretion disk, causing regular dips in the X-ray intensity. This eclipsing effect allows astronomers to study the system's geometry and better understand the properties of both the star and the black hole. The binary nature of Cygnus X-1 provides a unique laboratory for studying extreme physics. The system offers insights into the behavior of matter under intense gravitational fields, the processes of stellar evolution, and the mechanisms by which black holes grow and influence their surroundings. This cosmic pair continues to be a valuable source of information about some of the most extreme phenomena in our universe. Binary star systems offer a unique window into stellar evolution, allowing astronomers to study two stars of different masses that formed at the same time. In this particular binary system, we can observe how stars with varying sizes and compositions progress through their life cycles at different rates. The more massive star in the pair has already evolved into a red giant, expanding to many times its original size as it exhausts the hydrogen fuel in its core. This process occurs more rapidly in larger stars, demonstrating how stellar mass directly influences a star's lifespan. Meanwhile, its smaller companion remains in the main sequence stage, steadily fusing hydrogen in its core, much like our Sun. By comparing the two stars, scientists can refine models of stellar aging and validate theories about how factors like mass and chemical composition affect a star's evolution. The binary nature of the system also allows for precise measurements of stellar properties such as mass, radius, and temperature, which are crucial for understanding the inner workings of stars. Furthermore, this binary system provides insights into the future stages of stellar life. As the larger star continues to expand, it may eventually engulf its companion, leading to a common envelope phase or even a merger. These processes can result in the formation of unique stellar objects and potentially trigger supernova explosions, enriching the surrounding space with heavy elements essential for planet formation and life itself. Matter transfer between a companion star and a black hole is a fascinating process driven by the immense gravitational pull of the black hole. As the two objects orbit each other in a binary system, the black hole's gravity begins to strip away the outer layers of the companion star. This material does not immediately fall into the black hole, but instead forms a swirling disk of gas and dust around it, known as an accretion disk. The process begins when the companion star expands, often as it ages and enters its red giant phase. As the star grows, its outer layers extend beyond its Roche lobe, the region within which the star's gravity dominates. Once material crosses this boundary, it becomes more strongly influenced by the black hole's gravity and begins to be pulled away from the star. This stripped material spirals inward through the accretion disk, heating up due to friction and compression. As it gets closer to the black hole, it moves faster and becomes incredibly hot, often reaching temperatures of millions of degrees. This superheated material can emit intense radiation, particularly in the form of X-rays, making these binary systems some of the brightest X-ray sources in the universe. Eventually, some of this material will cross the black hole's event horizon and be consumed. However, not all the material ends up inside the black hole. Some of it can be ejected in powerful jets perpendicular to the accretion disk, while other portions may be blown away by intense radiation pressure. This complex interplay of gravity, radiation, and matter creates a dynamic and ever-changing system that continues to fascinate astronomers. Gravity is the central force orchestrating the intricate ballet between Cygnus X-1 and its companion star. This powerful force binds the two celestial bodies together, causing them to orbit a common center of mass. The immense gravitational pull of Cygnus X-1, a black hole with a mass about 15 times that of our Sun, exerts a dominant influence on its blue supergiant companion. The gravity of Cygnus X-1 is so intense that it actually distorts the shape of its companion star, pulling material from its outer layers into a swirling disk around the black hole. This process, known as accretion, is driven entirely by the black hole's gravitational field. As matter from the companion star spirals inward, it heats up to extreme temperatures, emitting powerful X-rays that allow us to detect and study this fascinating system. Gravity also determines the orbital period of this cosmic pair, which complete a full orbit around each other approximately every 5.5 days. The speed of this orbit, combined with the mass of the companion star, allows scientists to calculate the mass of Cygnus X-1 and confirm its nature as a black hole. Furthermore, the gravitational interaction between these two objects causes tidal forces that influence the evolution of both the black hole and its companion. Over time, these tidal effects can lead to changes in the orbit and the rate at which material is transferred from the star to the black hole, showcasing the dynamic nature of this cosmic partnership shaped by gravity. Cygnus X-1 emits X-rays due to its nature as a binary system containing a black hole. This system consists of a massive blue supergiant star orbiting an incredibly dense black hole. As the two objects dance around each other, the immense gravitational pull of the black hole draws material from its companion star. This material forms a swirling disk of gas and dust around the black hole, known as an accretion disk. As the matter in this disk spirals closer to the black hole, it becomes superheated due to friction and compression. The temperature in the inner regions of the accretion disk can reach millions of degrees. At these extreme temperatures, the disk emits a broad spectrum of electromagnetic radiation, including a significant amount of X-rays. These high-energy X-rays are a telltale sign of the intense processes occurring near the black hole's event horizon. Additionally, some of the infalling material may be ejected as powerful jets perpendicular to the accretion disk. These jets can also contribute to the X-ray emission, as particles within them are accelerated to nearly the speed of light and interact with surrounding matter and magnetic fields. X-ray emissions from space were first detected in the early 1960s during the dawn of the space age. Scientists and engineers, eager to explore the cosmos beyond Earth's atmosphere, launched a series of high-altitude rockets equipped with specialized detectors. These detectors were designed to capture high-energy radiation that cannot penetrate our planet's protective blanket of air. The breakthrough came in 1962 when a team led by Riccardo Giacconi launched a rocket carrying Geiger counters above the atmosphere. To their surprise, the instruments recorded a strong X-ray signal from a region in the constellation Scorpius. This unexpected discovery marked the birth of X-ray astronomy and opened a new window to observe the universe. Initially, researchers thought these emissions might be coming from the Moon, reflecting X-rays from the Sun. However, further observations revealed that the source was much more distant and far more energetic than anything in our solar system could produce. This realization sparked intense interest in the scientific community, leading to the development of more sophisticated X-ray detectors and dedicated space-based observatories. The detection of cosmic X-rays revolutionized our understanding of the universe. It revealed a cosmos filled with extreme objects and events invisible to traditional optical telescopes, including neutron stars, black holes, and the superheated gas in galaxy clusters. This discovery paved the way for a new era of multi-wavelength astronomy, allowing scientists to study the universe across the entire electromagnetic spectrum. X-ray emissions from Cygnus X-1 offer crucial insights into the nature of this remarkable cosmic object. These high-energy emissions reveal that Cygnus X-1 is a binary system consisting of a blue supergiant star orbiting an incredibly dense companion. The intense X-rays originate from the companion object, which scientists have identified as a stellar mass black hole. The X-ray data allows astronomers to study the behavior of matter as it falls towards the black hole. As gas from the blue supergiant is pulled towards its dark partner, it forms a swirling accretion disk. This disk heats up to extreme temperatures, causing it to emit X-rays that we can detect from Earth. The patterns and intensity of these emissions provide valuable information about the black hole's size, spin, and how it interacts with its environment. Furthermore, X-ray observations of Cygnus X-1 have revealed periodic fluctuations in brightness, occurring on timescales ranging from milliseconds to days. These variations offer clues about the complex processes taking place near the event horizon, the point of no return around a black hole. By analyzing these X-ray signals, scientists can test theories of general relativity and improve our understanding of how matter behaves in the most extreme conditions in the universe. Cygnus X-1's X-ray emissions have also played a crucial role in the broader field of black hole research. As one of the first discovered and most studied black hole systems, the X-ray data from Cygnus X-1 has helped shape our understanding of these enigmatic cosmic objects and continues to be a valuable source of information for astronomers and astrophysicists. Scientists employ specialized X-ray telescopes and detectors to measure and analyze X-ray emissions from distant cosmic sources. These instruments are typically mounted on satellites orbiting Earth to avoid atmospheric interference that would block incoming X-rays. One of the primary tools used is the Chandra X-ray Observatory, launched by NASA in 1999. Chandra uses highly polished mirrors to focus X-rays onto advanced detectors, creating detailed images and spectra of X-ray sources. These detectors can measure the energy, timing, and position of individual X-ray photons, providing a wealth of information about the emitting objects. Researchers also use other space-based observatories like XMM Newton and NuSTAR to gather complementary data. By combining observations from multiple telescopes, scientists can build a more comprehensive understanding of X-ray emitting phenomena. They analyze the collected data using sophisticated computer models and statistical techniques to interpret the physical processes occurring in these extreme environments. This analysis reveals crucial information about the temperature, density, and composition of X-ray emitting objects, as well as their motion and evolution over time. By studying these high-energy emissions, scientists gain valuable insights into some of the most energetic and extreme phenomena in the universe, from supernova remnants to the hot gas in galaxy clusters and the regions around black holes. Cygnus X-1 stands out as a pivotal source in the field of high-energy astrophysics. The X-ray variability observed in this system provides crucial insights into the nature of black holes and their interactions with surrounding matter. This binary system consists of a blue supergiant star orbiting a compact object, which astronomers have identified as a stellar mass black hole. The X-ray emissions from Cygnus X-1 fluctuate on timescales ranging from milliseconds to days, offering a wealth of information about the processes occurring near the black hole's event horizon. The rapid variability, particularly on millisecond timescales, indicates that the X-ray emitting region must be extremely compact, consistent with the presence of a black hole. These rapid fluctuations are thought to originate from the inner regions of the accretion disk, where material spirals inward at tremendous speeds before crossing the event horizon. Furthermore, the patterns of variability provide clues about the geometry of the accretion flow and the mechanisms by which energy is released. Studying these variations helps scientists better understand how black holes feed on surrounding matter and how they generate powerful jets of particles that can extend for thousands of light years into space. Cygnus X-1 stands out as one of the brightest X-ray sources in our galaxy, emitting an extraordinary amount of high-energy radiation. This cosmic powerhouse outshines many other X-ray emitters, producing a luminosity that can reach up to tens of thousands of times that of our Sun in the X-ray spectrum alone. Compared to other cosmic X-ray sources, Cygnus X-1 exhibits unique characteristics. Its X-ray emissions are highly variable, fluctuating on timescales as short as milliseconds. This rapid variability is a key feature that sets it apart from many other X-ray sources, such as supernova remnants or galaxy clusters, which tend to have more stable emission patterns. The spectrum of X-rays from Cygnus X-1 is also distinctive. It shows a combination of soft and hard X-rays, with the proportion changing over time. This spectral variability provides valuable insights into the physical processes occurring near the black hole at the heart of the system. Unlike diffuse X-ray sources, such as the hot gas in galaxy clusters, Cygnus X-1 is a point source, with its X-rays originating from a compact region around the black hole. This concentration of power in such a small area makes Cygnus X-1 an ideal laboratory for studying extreme physics and the behavior of matter in intense gravitational fields. The study of black hole emissions has revolutionized our understanding of these cosmic enigmas. By observing the radiation and particles ejected from the regions around black holes, scientists have gained crucial insights into their nature and behavior. One of the most significant discoveries is the confirmation of Hawking radiation, a theoretical prediction made by Stephen Hawking in the 1970s. This phenomenon suggests that black holes are not entirely black, but emit a faint glow of particles over time. While we cannot directly observe this radiation from distant black holes, its existence has been supported by observations of analog systems created in laboratories. Furthermore, the study of X-ray emissions from the accretion disks surrounding black holes has revealed important information about their spin and mass. These observations have allowed scientists to test and refine the predictions of general relativity in extreme gravitational environments. The detection of gravitational waves from merging black holes has provided additional confirmation of Einstein's theory and opened up an entirely new field of astronomy. Perhaps most intriguingly, the recent capture of the first image of a black hole shadow by the Event Horizon Telescope has given us visual confirmation of the existence of event horizons. This breakthrough has allowed scientists to directly study the behavior of matter and energy at the edge of a black hole, providing new tests for our theories of gravity and spacetime. Cygnus X-1 stands as a cosmic enigma that has pushed the boundaries of our understanding of stellar evolution. This powerful X-ray source, first discovered in 1964, is now known to be a binary system consisting of a blue supergiant star and an incredibly dense companion object. The companion's immense gravitational pull is so strong that it strips matter from the supergiant, creating a swirling accretion disk that emits intense X-rays. The challenge to our understanding comes from the nature of this companion object. Its estimated mass, about 14.5 times that of our Sun, exceeds what many scientists believed possible for a neutron star. This realization led to the groundbreaking conclusion that Cygnus X-1 harbors a stellar mass black hole, one of the first such objects to be identified. This discovery forced astrophysicists to reconsider the processes of stellar evolution and death. It raised questions about how such massive stars end their lives and under what conditions they might collapse directly into black holes rather than exploding as supernovae. Cygnus X-1 has thus become a crucial laboratory for studying the extreme physics of black holes and the final stages of massive stellar evolution. Moreover, the existence of Cygnus X-1 has implications for our understanding of gravitational waves, galaxy evolution, and the distribution of matter in the universe. It continues to be a source of new insights, challenging and refining our models of how the most massive stars in our universe live and die. Cygnus X-1, a well-known black hole in our galaxy, has intrigued astronomers since its discovery. Current theories suggest it formed from the collapse of a massive star in a binary system. This process likely occurred around 6 million years ago when a star roughly 40 times the mass of our Sun exhausted its nuclear fuel. As the star's core collapsed, it triggered a supernova explosion. However, unlike typical supernovae that completely destroy the star, this one was unusually weak. The result was a failed supernova, where most of the star's mass fell back onto the core, creating the black hole we observe today. The companion star, a blue supergiant, survived this cataclysmic event. It continues to orbit the black hole, feeding it with a steady stream of material. This interaction produces the powerful X-ray emissions that led to the initial detection of Cygnus X-1. Recent studies have also suggested that the black hole in Cygnus X-1 is spinning extremely rapidly, nearly at the maximum rate allowed by Einstein's theory of general relativity. This rapid spin provides clues about the black hole's formation process and the distribution of matter within the original star before it collapsed. Cygnus X-1, a well-known black hole in our galaxy, presents an intriguing puzzle in the realm of stellar evolution. This cosmic behemoth weighs in at about 21 times the mass of our Sun, making it one of the most massive stellar black holes ever discovered. Its extraordinary heft directly challenges our understanding of how black holes form from collapsing stars. The formation paradox arises because stars massive enough to create such hefty black holes should theoretically blow off much of their mass before collapsing. This mass loss occurs through powerful stellar winds and intense pulsations during the star's final stages of life. According to our current models, this process should limit the mass of the resulting black hole to no more than about 15 times that of our Sun. Yet Cygnus X-1 clearly exceeds this theoretical limit, forcing scientists to reconsider their models of stellar evolution and black hole formation. Some researchers propose that the progenitor star of Cygnus X-1 might have formed from the merger of two massive stars, allowing it to retain more mass. Others suggest that the star might have lived in an environment with a lower abundance of heavy elements, which would have resulted in weaker stellar winds and less mass loss. The existence of Cygnus X-1 and other similarly massive stellar black holes has sparked a flurry of new research and theories. As we continue to observe and study these cosmic giants, we edge closer to solving the formation paradox and deepening our understanding of the life cycles of the most massive stars in the universe. Metallicity plays a crucial role in the formation of massive stars and black holes. In astronomy, metals refer to all elements heavier than helium, and metallicity measures the abundance of these elements in a star or its environment. The amount of metals present during star formation significantly influences the characteristics and evolution of massive stars, ultimately affecting the types of black holes they may produce. In low metallicity environments, massive stars can form more easily and grow to larger sizes. This is because metals in stellar atmospheres increase opacity, making it harder for radiation to escape and limiting the star's growth. With fewer metals, stars can accrete more material and reach higher masses. These very massive, low metallicity stars are more likely to collapse directly into black holes at the end of their lives, potentially forming more massive black holes than their high metallicity counterparts. Conversely, high metallicity stars experience stronger stellar winds, which cause them to lose more mass throughout their lifetimes. This mass loss reduces the final mass of the star before it explodes as a supernova, often leaving behind a neutron star instead of a black hole. When black holes do form from high metallicity stars, they tend to be smaller. The relationship between metallicity and black hole formation has important implications for our understanding of gravitational wave events and the distribution of black hole masses across cosmic time. As the universe has become enriched with metals over billions of years, the typical masses of newly formed black holes may have changed, influencing the types of mergers we observe today. Cygnus X-1, a powerful X-ray source in the constellation Cygnus, has indeed challenged our understanding of stellar evolution. This system consists of a blue supergiant star orbiting an incredibly dense object, which scientists have identified as a black hole. The existence of such a massive black hole in a binary system forces us to reconsider some aspects of stellar life cycles. Traditionally, we thought that only the most massive stars, those exceeding 40 solar masses, could collapse directly into black holes at the end of their lives. However, Cygnus X-1 suggests that this process might occur in stars with lower initial masses. This revelation implies that the boundary between stars that form neutron stars and those that become black holes may be more fluid than previously believed. Furthermore, the presence of a black hole in such a young system raises questions about the speed of stellar evolution. The companion star in Cygnus X-1 is still in its supergiant phase, indicating that the black hole must have formed relatively quickly. This rapid evolution challenges our models of how long it takes for massive stars to exhaust their fuel and collapse. The study of Cygnus X-1 also highlights the importance of binary star systems in shaping stellar evolution. The interaction between the two stars in this system likely played a crucial role in the formation of the black hole. As a result, astronomers now recognize that we need to consider not just individual stellar evolution, but also the complex dynamics of binary and multiple star systems to fully understand the life cycles of stars and the formation of exotic objects like black holes. Cygnus X-1, the first black hole ever discovered, has profound implications for our understanding of galaxy formation. This stellar mass black hole, located in our own Milky Way galaxy, serves as a crucial piece in the puzzle of how galaxies evolve over cosmic time. The existence of Cygnus X-1 supports the idea that black holes are common throughout the universe. This realization has led astronomers to propose that supermassive black holes, millions or billions of times more massive than Cygnus X-1, might play a central role in galaxy formation and evolution. These cosmic giants are now thought to reside at the hearts of most, if not all, large galaxies. The relationship between black holes and their host galaxies appears to be symbiotic. As galaxies grow, their central black holes also increase in mass by consuming surrounding matter. In turn, the energy released by this process can regulate star formation within the galaxy. This feedback mechanism helps explain why we observe a correlation between the mass of a galaxy's central black hole and the galaxy's overall mass. Furthermore, the study of Cygnus X-1 and similar objects has improved our understanding of how matter behaves in extreme gravitational environments. This knowledge informs models of how gas and dust are accreted onto supermassive black holes in the early universe, potentially explaining the rapid growth of both black holes and galaxies in the cosmic dawn. As we continue to study Cygnus X-1 and its counterparts, we refine our models of galaxy formation, painting a more accurate picture of the cosmic landscape. Cygnus X-1 stands as a remarkable cosmic entity that pushes the boundaries of our understanding of stellar evolution and black hole formation. This extraordinary system consists of a massive blue supergiant star orbiting an incredibly dense, invisible companion that astronomers have identified as a stellar mass black hole. The black hole in Cygnus X-1 is estimated to have a mass of around 15 times that of our Sun, which is significantly higher than what traditional stellar evolution models predicted for the end state of massive stars. This unexpected mass challenges our previous notions about the upper limit for stellar masses and the processes that lead to black hole formation. Conventional wisdom suggested that stars above a certain mass would lose much of their material through powerful stellar winds before they could collapse into black holes. However, the existence of Cygnus X-1 indicates that some stars can retain more of their mass throughout their lives than previously thought, allowing them to form larger black holes upon their demise. This discovery has profound implications for our understanding of stellar life cycles, black hole populations, and even the gravitational waves detected from black hole mergers. Cygnus X-1 serves as a cosmic laboratory, compelling scientists to refine their models and expand their comprehension of the most massive objects in our universe. Astronomers employ a variety of telescopes to study Cygnus X-1, each designed to capture different types of electromagnetic radiation emitted by this fascinating cosmic object. Radio telescopes detect the low-energy radio waves emanating from the system, providing valuable data about its structure and behavior. These large dish antennas, often arranged in arrays, can reveal details about the jets of material expelled from the black hole. Optical telescopes, both on the ground and in space, observe Cygnus X-1 in visible light. While the black hole itself cannot be seen, these instruments can study the companion star and the surrounding gas and dust. The Hubble Space Telescope, for instance, has contributed significantly to our understanding of this system. X-ray telescopes play a crucial role in studying Cygnus X-1, as black holes are powerful emitters of X-rays. Satellites like the Chandra X-ray Observatory and XMM Newton have provided high-resolution images and spectra, allowing scientists to probe the extreme environment near the black hole. These observations help reveal the temperature and composition of the hot gas swirling around the black hole, as well as the intensity of its gravitational field. Gamma-ray telescopes, such as the Fermi Gamma-ray Space Telescope, detect the highest energy radiation from Cygnus X-1. These observations provide insights into the most energetic processes occurring in the system, including particle acceleration in the jets and the interaction between the black hole and its companion star. Radio telescopes have played a crucial role in unraveling the mysteries of Cygnus X-1, a cosmic powerhouse that has captivated astronomers for decades. These sophisticated instruments detect radio waves emitted by celestial objects, allowing scientists to peer into regions of space that are otherwise invisible to optical telescopes. In the case of Cygnus X-1, radio telescopes have revealed intricate details about its structure and behavior. They have helped astronomers map out the powerful jets of material that stream away from the black hole at nearly the speed of light. These jets, composed of charged particles, emit radio waves that can be detected and analyzed, providing valuable information about the extreme environment around the black hole. Furthermore, radio observations have enabled scientists to measure the size and shape of the accretion disk surrounding Cygnus X-1. This disk of superheated gas swirls around the black hole, and its radio emissions offer clues about the temperature, density, and motion of the material as it spirals inward. By studying these characteristics, astronomers can better understand the processes that drive the incredible energy output of this cosmic behemoth. Perhaps most importantly, radio telescopes have contributed to confirming the presence of a black hole in Cygnus X-1. By combining radio data with observations from other wavelengths, scientists have built a comprehensive picture of this system, including precise measurements of its mass and spin. These findings have solidified Cygnus X-1's status as one of the most well-studied black holes in our galaxy, advancing our understanding of these enigmatic cosmic objects. Space-based observatories have revolutionized our understanding of Cygnus X-1, one of the most famous black hole systems in our galaxy. These advanced telescopes, orbiting high above Earth's atmosphere, provide unparalleled views of this cosmic powerhouse. Cygnus X-1 is a binary system consisting of a blue supergiant star and a black hole locked in a cosmic dance. Space observatories equipped with X-ray and gamma-ray detectors are crucial for studying this system, as these high-energy emissions are largely blocked by Earth's atmosphere. These observatories can detect the intense radiation produced as matter from the star falls into the black hole, forming a swirling accretion disk. Instruments like the Chandra X-ray Observatory and the now-retired Compton Gamma Ray Observatory have provided detailed data on the energy spectrum and variability of Cygnus X-1. This information helps scientists understand the physics of black holes, including how they consume matter and release energy. Space-based observatories also allow for long-term monitoring of the system, revealing changes in its behavior over time. Furthermore, these orbital platforms enable astronomers to study Cygnus X-1 across multiple wavelengths simultaneously, from radio waves to gamma rays. This multi-wavelength approach provides a comprehensive picture of the complex processes occurring in and around the black hole, advancing our knowledge of these extreme cosmic objects. The Chandra X-ray Observatory has been instrumental in expanding our understanding of Cygnus X-1, one of the most studied objects in our galaxy. This remarkable space telescope has provided unprecedented insights into the nature of this famous black hole system, revealing details that were previously hidden from view. Chandra's high-resolution X-ray vision has allowed astronomers to peer into the heart of Cygnus X-1, observing the intense X-ray emissions produced as matter from its companion star is pulled into the black hole. These observations have helped scientists measure the spin of the black hole with greater precision, a crucial parameter in understanding its behavior and evolution. Furthermore, Chandra has enabled researchers to study the powerful jets of material ejected from the vicinity of the black hole. These observations have shed light on the complex interactions between the black hole, its accretion disk, and the surrounding space, providing valuable data on how black holes influence their environments. The observatory has also contributed to our knowledge of the wind from the companion star in the Cygnus X-1 system. By analyzing the X-ray spectrum, scientists have gained insights into the composition and dynamics of this stellar wind, which plays a crucial role in feeding material to the black hole. These findings have improved our overall understanding of how binary systems containing black holes evolve and interact over time. Interferometry is a powerful technique used in astronomy to combine signals from multiple telescopes, effectively creating a much larger virtual telescope. This method allows scientists to achieve incredibly high-resolution observations far beyond what a single telescope could accomplish. By precisely measuring the differences in arrival times of light waves at different telescopes, astronomers can create detailed images and gather precise data about distant cosmic objects. In the case of Cygnus X-1, interferometry has been crucial in unraveling the mysteries of this famous black hole system. Cygnus X-1 consists of a black hole orbiting a blue supergiant star, and interferometric observations have allowed astronomers to measure its properties with unprecedented accuracy. By using radio interferometry, scientists have been able to track the motion of jets of material expelled from the vicinity of the black hole, providing valuable insights into its behavior and environment. Optical interferometry has also played a role in studying Cygnus X-1, enabling researchers to measure the system's distance from Earth more precisely. This information is critical for calculating the black hole's mass and other physical characteristics. The improved resolution provided by interferometric techniques has allowed astronomers to study the accretion disk surrounding the black hole in greater detail, revealing how matter behaves in the extreme gravitational environment near a black hole. These interferometric observations of Cygnus X-1 have significantly advanced our understanding of black holes and their effects on surrounding space. The technique continues to be refined and expanded, promising even more detailed insights into this and other cosmic phenomena in the future. Gravitational wave detectors have revolutionized our ability to study compact objects like Cygnus X-1, offering a new window into the universe. These detectors, such as the Laser Interferometer Gravitational Wave Observatory, known as LIGO, can detect ripples in spacetime caused by massive cosmic events. For objects like Cygnus X-1, which is believed to be a black hole in a binary system with a blue supergiant star, gravitational wave detectors provide crucial complementary data to traditional electromagnetic observations. While we cannot directly detect gravitational waves from the stable orbit of Cygnus X-1, these detectors are vital for studying similar systems and understanding the physics of black holes in general. When black holes in binary systems merge, they produce powerful gravitational waves that can be detected by LIGO and other detectors. By analyzing these signals, scientists can infer the masses, spins, and other properties of the merging black holes. This information helps refine our models of how systems like Cygnus X-1 evolve over time and what their ultimate fate might be. Moreover, gravitational wave detections from other black hole mergers provide valuable insights into the population of black holes in the universe. This broader context enhances our understanding of objects like Cygnus X-1, allowing scientists to place them within the larger cosmic narrative of black hole formation and evolution. Future observational technologies hold great promise for enhancing our ability to study Cygnus X-1, the first black hole candidate ever discovered. Advanced space-based X-ray telescopes with improved sensitivity and resolution will allow us to observe the accretion disk around the black hole in unprecedented detail. These instruments could reveal the complex dynamics of matter as it spirals towards the event horizon, providing new insights into the extreme physics at play. Gravitational wave detectors, both on Earth and in space, will open up an entirely new avenue for studying Cygnus X-1. By detecting the ripples in spacetime caused by the black hole's interaction with its companion star, we could gain valuable information about the system's mass, spin, and evolution over time. This data would complement our existing electromagnetic observations, offering a more complete picture of this fascinating binary system. Next-generation radio telescopes, such as large arrays of dishes spread across continents or even in space, could dramatically improve our ability to create high-resolution images of the region around Cygnus X-1. These advanced interferometers might allow us to directly observe the shadow cast by the black hole against the bright background of accreting material, providing a stringent test of general relativity in the strong field regime. Neutrino detectors, while not specifically designed for studying black holes, could potentially detect neutrinos produced in the hot, dense environment near Cygnus X-1. This would offer a unique probe of the physical conditions in the vicinity of the black hole, complementing our observations across the electromagnetic spectrum and through gravitational waves. Stephen Hawking and Kip Thorne, two renowned physicists, engaged in a fascinating wager concerning Cygnus X-1, a celestial object that captivated the scientific community. Their bet, made in 1974, centered on the nature of this mysterious cosmic entity. Hawking bet against the existence of black holes, arguing that Cygnus X-1 was not a black hole. Thorne, on the other hand, was confident that it was indeed a black hole. The stakes were unusual, yet fitting for these brilliant minds. If Hawking won, he would receive a one-year subscription to Private Eye, a British satirical magazine. If Thorne emerged victorious, he would be awarded a 4-year subscription to Penthouse magazine. This friendly wager highlighted the uncertainty surrounding black holes at the time. Cygnus X-1, discovered in 1964, exhibited properties that suggested it might be a black hole, but conclusive evidence was lacking. The bet also underscored the playful nature of scientific discourse and the willingness of scientists to challenge their own theories. Interestingly, Hawking conceded the bet in 1990, as mounting evidence supported the idea that Cygnus X-1 was indeed a black hole. This concession marked a significant shift in our understanding of these cosmic phenomena and demonstrated the importance of scientific humility in the face of new evidence. The discovery of Cygnus X-1 in 1964 sent shockwaves through the scientific community, challenging long-held beliefs about the nature of our universe. This powerful source of X-rays, located in the constellation Cygnus, defied explanation, using conventional theories of stellar evolution and behavior. As astronomers studied Cygnus X-1 more closely, they realized they were observing something extraordinary. The object was emitting an enormous amount of energy from an incredibly small area, far more than could be explained by normal stellar processes. This led to a radical proposal. Cygnus X-1 might be a black hole, an object so dense that not even light could escape its gravitational pull. The idea of black holes had been around for decades, proposed as a mathematical solution to Einstein's equations of general relativity. However, many scientists considered them purely theoretical, doubting such extreme objects could exist in reality. Cygnus X-1 forced the scientific community to confront the possibility that these cosmic monsters were not just mathematical curiosities, but actual physical entities lurking in our galaxy. This realization sparked intense debate and research. Some scientists eagerly embraced the black hole interpretation, while others sought alternative explanations. The controversy surrounding Cygnus X-1 ultimately led to significant advancements in our understanding of extreme astrophysical objects and the fundamental nature of space and time. When astronomers first detected Cygnus X-1 in the 1960s, they were puzzled by its intense X-ray emissions. Several alternative explanations were proposed before the scientific community settled on the now accepted idea of a black hole. One early theory suggested that Cygnus X-1 might be a neutron star, an incredibly dense stellar remnant formed after a massive star's supernova. Neutron stars were known to emit X-rays, but the sheer intensity of Cygnus X-1's emissions challenged this explanation. Another hypothesis proposed that the X-rays might be coming from a white dwarf star accreting matter from a companion. This scenario, known as a cataclysmic variable, could produce X-rays, but not at the observed levels of Cygnus X-1. Some scientists even speculated that the X-ray source might be a cluster of lower-mass objects or an as-yet unknown type of celestial body. However, as more data was collected and analyzed, these alternative explanations were gradually ruled out, leading to the current understanding of Cygnus X-1 as a black hole in a binary system with a blue supergiant star. The journey to accepting Cygnus X-1 as a black hole was a gradual process that unfolded over several decades. When this powerful X-ray source was first discovered in 1964, astronomers were unsure about its true nature. The concept of black holes was still largely theoretical at the time, and many scientists were skeptical about their existence in reality. Throughout the 1970s, evidence began to accumulate, suggesting that Cygnus X-1 might indeed be a black hole. Observations revealed that it was part of a binary system with a massive blue supergiant star, and its X-ray emissions showed rapid variability, indicating a compact object. However, alternative explanations, such as neutron stars, were still considered possible. The debate intensified in the 1980s and 90s as more sophisticated observational techniques became available. Measurements of the system's mass suggested that the compact object was too massive to be a neutron star, strengthening the case for a black hole. Yet, some astronomers remained unconvinced, arguing that our understanding of stellar evolution and compact objects might be incomplete. It wasn't until the early 2000s that a broad consensus began to form within the scientific community. Improved observations and theoretical models provided compelling evidence that Cygnus X-1 was indeed a black hole. By 2011, when detailed studies of the system's mass and other properties were published, the majority of astronomers accepted Cygnus X-1 as one of the most convincing examples of a stellar mass black hole in our galaxy. Cygnus X-1's true nature as a black hole was confirmed through decades of careful observations and analysis. Early skeptics were gradually won over by mounting evidence from multiple sources. Radio and X-ray observations revealed an incredibly compact, massive object orbiting a blue supergiant star. This object was far too dense to be a neutron star or any other known celestial body. Precise measurements of the system's orbital motions allowed astronomers to calculate that the invisible companion had a mass at least 6 times that of our Sun. This firmly placed it above the theoretical maximum mass for a neutron star, leaving a black hole as the only viable explanation. Additionally, the detection of powerful jets of material being ejected at nearly the speed of light provided further support for the presence of a black hole's intense gravitational field. Perhaps most convincingly, observations of X-ray emissions from the system match theoretical predictions for matter falling into a black hole. The spectrum and variability of these emissions could only be explained by the extreme physics occurring near a black hole's event horizon. As technology improved, astronomers were even able to detect gravitational waves from similar systems, providing independent confirmation of stellar mass black holes' existence. The discovery of Cygnus X-1 in 1964 marked a pivotal moment in black hole research, propelling the field from theoretical musings to observational science. As the first strong candidate for a stellar mass black hole, Cygnus X-1 provided astronomers with a tangible target to study, enabling them to test and refine their theories about these enigmatic cosmic objects. This binary system, consisting of a blue supergiant star and an invisible companion, exhibited intense X-ray emissions that could not be explained by conventional stellar processes. The invisible object's immense gravitational pull on its companion star suggested a compact object far more massive than a neutron star, leaving a black hole as the most plausible explanation. The study of Cygnus X-1 led to significant advancements in our understanding of accretion disks, the swirling matter that surrounds black holes. Observations of this system helped scientists develop models of how matter behaves in extreme gravitational fields, providing insights into the mechanisms that power some of the most energetic phenomena in the universe. Furthermore, Cygnus X-1 spurred the development of new observational techniques and technologies. The need to study this object across multiple wavelengths encouraged collaboration between different branches of astronomy, setting a precedent for the multi-messenger approach that now characterizes modern astrophysics. This discovery not only confirmed the existence of black holes, but also opened up a new frontier in our exploration of the cosmos. The debates surrounding Cygnus X-1 offer valuable insights into the scientific process and the evolution of our understanding of black holes. Discovered in 1964, Cygnus X-1 sparked intense discussions among astronomers and physicists as they grappled with its true nature. Initially, scientists were skeptical about the existence of black holes, viewing them as mathematical curiosities rather than real cosmic objects. The observations of Cygnus X-1, however, provided compelling evidence for a massive, compact object that could only be explained by the presence of a black hole. This forced the scientific community to confront the reality of these extreme cosmic phenomena. The Cygnus X-1 debates also highlight the importance of technological advancements in scientific discovery. As observational techniques improved, researchers gathered more data, gradually building a stronger case for the black hole interpretation. This underscores how progress in science often depends on our ability to observe and measure phenomena with increasing precision. Perhaps most importantly, the Cygnus X-1 discussions demonstrate the value of healthy scientific skepticism and the power of evidence-based consensus. Even renowned physicists like Stephen Hawking, who initially bet against Cygnus X-1 being a black hole, eventually changed their views in light of overwhelming evidence. This willingness to adapt theories based on new data is a cornerstone of scientific progress and a lesson that extends far beyond astrophysics. Cygnus X-1 stands as a cosmic testbed for Einstein's theory of general relativity, offering scientists a unique opportunity to study the behavior of gravity in extreme conditions. This binary star system consists of a blue supergiant star orbiting a black hole, creating an ideal environment to observe relativistic effects. The intense gravitational field of the black hole in Cygnus X-1 warps spacetime dramatically, allowing researchers to measure phenomena predicted by general relativity. As matter from the companion star falls toward the black hole, it forms an accretion disk that emits powerful X-rays. These emissions provide valuable data about the structure of spacetime near the black hole's event horizon. One key aspect of general relativity that Cygnus X-1 helps scientists investigate is the no-hair theorem, which posits that black holes can be completely described by just three properties: mass, spin, and electric charge. By studying the X-ray emissions and the orbital dynamics of the binary system, researchers can test this fundamental principle and search for any deviations that might suggest modifications to our understanding of gravity. Furthermore, Cygnus X-1 allows scientists to probe the limits of general relativity in the strong field regime, where gravitational effects are most pronounced. This provides crucial insights into the behavior of gravity under extreme conditions, helping to bridge the gap between general relativity and quantum mechanics, and potentially paving the way for a unified theory of quantum gravity. General relativity has been put to the test through observations of Cygnus X-1, a binary system consisting of a blue supergiant star and a black hole. This cosmic laboratory has provided strong evidence for several key predictions of Einstein's theory. One crucial confirmation is the existence of an event horizon around the black hole. As matter from the companion star spirals towards the black hole, it forms an accretion disk that emits powerful X-rays. These emissions abruptly cut off at a specific radius, indicating the presence of an event horizon beyond which nothing can escape. The intense gravitational field of the black hole in Cygnus X-1 also causes significant time dilation, another prediction of general relativity. Clocks near the black hole would tick more slowly compared to those farther away, an effect that has been indirectly observed through the behavior of infalling matter and the emission of X-rays. Furthermore, studies of Cygnus X-1 have supported the no-hair theorem, which states that black holes can be completely described by just three properties: mass, spin, and electric charge. The simplicity of the black hole's structure, despite its complex origins, aligns perfectly with this fundamental prediction of general relativity. The extreme gravity of Cygnus X-1, a stellar mass black hole, dramatically warps the fabric of spacetime in its vicinity. This warping causes time to flow more slowly near the black hole compared to regions farther away, a phenomenon known as gravitational time dilation. As we approach the event horizon of Cygnus X-1, time slows down significantly relative to an outside observer. For objects or hypothetical observers very close to Cygnus X-1, time would pass much more slowly than for those at a greater distance. This effect becomes more pronounced the closer one gets to the black hole. Near the event horizon, time dilation reaches extreme levels, with time nearly stopping from an outside perspective. This time dilation has fascinating implications. If we could observe an object falling towards Cygnus X-1, it would appear to move more slowly as it approached the event horizon. From the perspective of the falling object, however, time would seem to pass normally, while the outside universe would appear to speed up. The intense gravity of Cygnus X-1 not only affects time, but also bends light paths. This gravitational lensing, combined with time dilation, creates a distorted view of the space around the black hole, making it a cosmic laboratory for testing our understanding of extreme gravitational environments and the nature of space-time itself. Gravitational lensing is a fascinating phenomenon that occurs when the gravity of a massive object bends the path of light from a distant source. This effect can magnify, distort, or even create multiple images of the original light source. It's like looking through a giant cosmic magnifying glass, allowing astronomers to observe objects that would otherwise be too faint or distant to detect. In the case of Cygnus X-1, a well-known black hole system, gravitational lensing could potentially play an intriguing role. While Cygnus X-1 itself is not massive enough to create significant lensing effects, it could be affected by the lensing caused by other objects along our line of sight. This might alter our observations of the system, potentially magnifying its brightness or creating subtle distortions in its appearance. Moreover, the intense gravitational field of Cygnus X-1's black hole could create a localized lensing effect, bending light from its companion star or its own accretion disk. This could provide valuable information about the black hole's properties and the extreme environment surrounding it. Studying gravitational lensing in relation to systems like Cygnus X-1 allows scientists to probe the nature of gravity in extreme conditions, test Einstein's theory of general relativity, and gain insights into the distribution of matter in the universe. As our observational techniques improve, we may uncover even more ways in which gravitational lensing enhances our understanding of these enigmatic cosmic objects. Cygnus X-1 has played a pivotal role in advancing our understanding of space-time and the extreme physics of black holes. As one of the first discovered black hole candidates, this binary system consists of a blue supergiant star orbiting an invisible companion that scientists believe to be a stellar mass black hole. The study of Cygnus X-1 has provided crucial evidence supporting Einstein's theory of general relativity, which describes gravity as a curvature of spacetime. By observing the behavior of matter and energy around this black hole, scientists have been able to test and confirm predictions about how spacetime behaves in extreme gravitational environments. One key contribution of Cygnus X-1 research is the observation of frame dragging, a phenomenon where a rotating black hole pulls spacetime around with it. This effect, also known as the lens-thirring effect, demonstrates how massive objects can influence the very fabric of spacetime, a concept central to our modern understanding of gravity and the universe. Furthermore, studies of Cygnus X-1 have helped scientists refine models of accretion disks, the swirling matter surrounding black holes. These observations have shed light on how spacetime behaves near the event horizon, the boundary beyond which nothing can escape the black hole's gravitational pull. This research continues to push the boundaries of our knowledge about the nature of space, time, and gravity in the most extreme conditions found in the universe. General relativity, Einstein's groundbreaking theory of gravity, has been extensively tested in various cosmic settings. However, the extreme environment of Cygnus X-1, a well-known black hole system, presents unique opportunities for further investigation. One key aspect of general relativity that remains challenging to test in Cygnus X-1 is the behavior of spacetime very close to the event horizon. While we can observe the effects of the black hole on its companion star and surrounding matter, directly probing the spacetime just outside the event horizon remains elusive. This region, where gravity is incredibly strong, could potentially reveal deviations from general relativity or confirm its predictions with unprecedented precision. Another area of interest is the frame dragging effect, also known as the lens thirring effect. This phenomenon, predicted by general relativity, describes how a rotating black hole drags spacetime around with it. While evidence for frame dragging has been observed in other systems, measuring its precise strength and behavior in the extreme gravitational field of Cygnus X-1 could provide valuable insights. The properties of gravitational waves emitted by the Cygnus X-1 system also present an opportunity for testing general relativity. As our gravitational wave detection capabilities improve, we may be able to observe and analyze the gravitational waves produced by the black hole and its companion star, potentially uncovering new aspects of gravitational physics in extreme conditions. Cygnus X-1, the first discovered black hole candidate, continues to be a crucial testing ground for Einstein's theories of gravity. Future observations of this system could provide even more stringent tests of general relativity in extreme gravitational environments. Advanced gravitational wave detectors might soon be able to detect the continuous waves emitted by Cygnus X-1 as it spirals closer to its companion star. These waves, if detected, would offer unprecedented insights into the behavior of spacetime near black holes, potentially revealing deviations from Einstein's predictions or confirming them with greater precision. X-ray and radio observations of the accretion disk around Cygnus X-1 could help scientists probe the innermost stable circular orbit, a key prediction of general relativity. By studying the emission from matter just before it plunges into the black hole, researchers might be able to test whether spacetime behaves as Einstein's equations suggest in these extreme conditions. Furthermore, long-term monitoring of the orbital dynamics of the Cygnus X-1 system could reveal subtle effects predicted by general relativity, such as the precession of the orbit due to frame dragging. These observations would provide a unique opportunity to test Einstein's theories in a regime where the effects of both special and general relativity are significant, potentially uncovering new physics or further cementing Einstein's legacy. Relativistic jets are powerful streams of particles and energy that shoot out from the poles of certain celestial objects at nearly the speed of light. These jets can extend for thousands or even millions of light years into space, making them some of the largest known structures in the universe. They are typically associated with active galactic nuclei, where supermassive black holes reside at the centers of galaxies, but they can also occur in smaller-scale systems like binary star systems containing stellar mass black holes. Cygnus X-1 is a prime example of a binary system that produces relativistic jets. It consists of a blue supergiant star orbiting a black hole that is about 15 times the mass of our Sun. As material from the star falls toward the black hole, it forms an accretion disk, a swirling vortex of superheated gas. Some of this material does not fall into the black hole, but instead gets accelerated and ejected as jets from the poles of the black hole. The jets from Cygnus X-1 were first detected in the 1970s, making it one of the earliest known sources of relativistic jets in our galaxy. These jets are thought to be powered by the intense gravitational and magnetic fields around the black hole, which accelerate particles to extreme speeds. The study of Cygnus X-1 has been crucial in understanding the mechanisms behind jet formation and the behavior of matter in the extreme conditions near black holes. Observations of Cygnus X-1 have revealed that its jets can vary in strength and direction over time, providing valuable insights into the dynamic nature of these phenomena. This binary system serves as a cosmic laboratory, allowing scientists to test theories about black hole physics, relativistic jet formation, and the extreme environments that exist in the universe. Cygnus X-1, a well-known black hole in our galaxy, produces powerful jets that are both similar to and distinct from those of other cosmic objects. These jets, composed of high-energy particles, shoot out from the black hole at nearly the speed of light, extending for thousands of light years into space. Compared to jets from other black holes, the jets from Cygnus X-1 are relatively stable and persistent. Many black holes exhibit intermittent jet activity, but Cygnus X-1 maintains a steady outflow. This consistency allows scientists to study these jets in great detail, providing valuable insights into the mechanisms that drive such phenomena. The jets from Cygnus X-1 are also remarkably powerful when compared to those from neutron stars or white dwarfs. The immense gravitational pull of the black hole accelerates particles to extreme velocities, resulting in jets that are more energetic and extend further into space than those produced by less massive objects. However, when compared to the jets from supermassive black holes at the centers of galaxies, the jets from Cygnus X-1 are considerably smaller in scale. While still impressive, they pale in comparison to the massive jets that can extend for millions of light-years from galactic cores, influencing the evolution of entire galaxies and clusters. The jets we observe in space are primarily composed of energetic particles and electromagnetic radiation. These powerful streams of matter and energy are typically made up of electrons, protons, and other subatomic particles accelerated to incredibly high speeds, often approaching the speed of light. In some cases, the jets also contain heavier atomic nuclei and even trace amounts of neutral atoms. The exact composition of these jets can vary depending on their source. For instance, jets emanating from active galactic nuclei, which are powered by supermassive black holes at the centers of galaxies, tend to be rich in electrons and positrons. These particles are accelerated by intense magnetic fields and extreme gravitational forces near the black hole. In contrast, jets associated with young stellar objects or protostars might contain a higher proportion of ionized atoms and molecules. These jets play a crucial role in the star formation process, carrying away excess angular momentum and helping to regulate the growth of the nascent star. Regardless of their origin, these jets also emit various forms of electromagnetic radiation, including radio waves, visible light, X-rays, and sometimes even gamma rays. This radiation provides astronomers with valuable information about the physical processes occurring within the jets and their source objects, allowing us to study these fascinating phenomena from vast distances across the cosmos. As these powerful jets stream away from active galactic nuclei, they encounter the interstellar medium, creating a complex and dynamic interaction. The jets, composed of high-energy particles traveling at nearly the speed of light, slam into the relatively stationary gas and dust of the interstellar space. This collision generates intense shock waves that compress and heat the surrounding material to extreme temperatures. The impact of these jets can have far-reaching effects on their galactic environment. As they propagate through space, they can create vast bubbles or cavities in the interstellar medium, effectively sweeping away gas and dust from their path. This process, known as jet-induced feedback, can significantly influence the distribution of matter in the galaxy and even affect star formation rates in regions far from the central black hole. Moreover, the interaction between the jets and the interstellar medium can produce spectacular visual phenomena. As the jets plow through space, they can create intricate structures such as lobes, hotspots, and filaments that are visible across multiple wavelengths of light. These structures often extend far beyond the boundaries of their host galaxies, spanning hundreds of thousands of light-years. The study of these jet-medium interactions provides valuable insights into the energy transfer processes in galaxies and the role of active galactic nuclei in shaping galactic evolution. By observing the effects of these jets on their surroundings, astronomers can better understand the complex interplay between supermassive black holes and the galaxies they inhabit. Studying the powerful jets emitted by black holes provides astronomers with invaluable insights into the extreme physics at play in these cosmic behemoths. These jets, composed of high-energy particles and radiation, offer a window into the inner workings of black holes and their immediate surroundings. By observing these jets, scientists can better understand the process of accretion, where matter falls into the black hole. The jets are thought to be powered by the energy released as this material spirals inward, heating up to incredible temperatures. This gives us clues about how black holes feed and grow over time. The jets also reveal information about the strong magnetic fields around black holes. These fields are believed to play a crucial role in launching and shaping the jets, and studying their behavior helps refine our models of black hole physics. Additionally, the composition and structure of the jets provide data on how matter behaves in the presence of extreme gravity. Furthermore, these jets allow scientists to test Einstein's theory of general relativity in the most extreme conditions known in the universe. By examining how the jets interact with their environment and how they change over time, researchers can probe the limits of our current understanding of gravity and potentially uncover new physics beyond our standard models. Cygnus X-1, a powerful X-ray source, is known for its impressive relativistic jets that extend far into space. These jets, composed of high-energy particles, dramatically influence the surrounding cosmic environment. As they blast outward at nearly the speed of light, they interact with nearby gas and dust, creating shock waves and heating the interstellar medium. The jets from Cygnus X-1 carve out massive bubbles in the surrounding space, pushing aside and compressing nearby gas clouds. This compression can trigger star formation in these regions, potentially giving birth to new stellar objects. The intense radiation from the jets also ionizes nearby gas, creating glowing regions that can be observed by telescopes. Furthermore, these jets contribute to the distribution of heavy elements throughout the galaxy. As the jets interact with the interstellar medium, they spread materials that were originally formed near the black hole, enriching distant regions of space with these elements. This process plays a crucial role in the chemical evolution of the galaxy. The impact of Cygnus X-1's jets extends well beyond its immediate vicinity, influencing the dynamics and composition of the interstellar medium on a larger scale. By studying these effects, scientists gain valuable insights into the complex interactions between black holes and their galactic environments. Astronomers employ a variety of sophisticated technologies to observe and study high-energy jets from active galactic nuclei. Radio telescopes play a crucial role in detecting the synchrotron radiation emitted by electrons spiraling through magnetic fields in these jets. Large arrays of radio telescopes, such as the Very Large Array in New Mexico, work together to create high-resolution images of jet structures. X-ray observatories, like the Chandra X-ray Observatory and XMM Newton, are essential for studying the hottest and most energetic regions of these jets. These space-based telescopes can detect the intense X-ray emission produced by particles accelerated to nearly the speed of light within the jets. Gamma-ray telescopes, both ground-based and space-based, are used to observe the most extreme high-energy emissions from these jets. The Fermi Gamma-ray Space Telescope and ground-based facilities like Veritas and MAGIC can detect gamma rays produced by the interaction of jet particles with surrounding radiation fields. Optical and infrared telescopes also contribute to our understanding of jets by observing the host galaxies and the regions where jets interact with surrounding gas and dust. Advanced computer simulations and modeling techniques are then used to interpret this wealth of observational data, helping scientists piece together a comprehensive picture of these powerful cosmic phenomena. Cygnus X-1, a powerful black hole in our galaxy, exerts a significant influence on its cosmic neighborhood. This celestial behemoth, with a mass about 15 times that of our Sun, creates a gravitational field so intense that it warps the very fabric of space and time around it. The immense gravitational pull of Cygnus X-1 affects nearby stars in dramatic ways. It can strip away the outer layers of stars that venture too close, pulling their material into a swirling accretion disk around the black hole. This process heats the gas to extreme temperatures, causing it to emit intense X-rays that we can detect from Earth. Cygnus X-1 also impacts surrounding gas clouds. Its powerful gravitational field can compress nearby clouds of interstellar gas, potentially triggering the formation of new stars. Additionally, the black hole generates powerful jets of particles that shoot out from its poles at nearly the speed of light. These jets can travel vast distances, interacting with and heating the interstellar medium. The interactions between Cygnus X-1 and its environment provide astronomers with a unique laboratory for studying the extreme physics of black holes and their effects on cosmic matter. By observing these processes, scientists continue to refine our understanding of the fundamental forces shaping our universe. Cygnus X-1, a powerful black hole in our Milky Way galaxy, exerts a tremendous gravitational influence on its surroundings. This cosmic behemoth, with a mass about 15 times that of our Sun, creates a significant warping of space-time in its vicinity. The black hole's gravitational pull is so intense that it affects everything within several light-years of its location. The most immediate and dramatic impact of Cygnus X-1's gravity is on its companion star. This blue supergiant, locked in a cosmic dance with the black hole, is slowly being stripped of its outer layers. The intense gravitational forces pull material from the star, forming an accretion disk around the black hole. This process not only shapes the fate of the companion star, but also influences the distribution of gas and dust in the surrounding space. Beyond its immediate binary system, Cygnus X-1's gravity affects the motion and distribution of nearby stars and interstellar matter. Its presence can alter the orbits of stars and affect the formation of new stellar bodies in the region. The black hole's influence extends to several parsecs, subtly shaping the structure of this part of the Milky Way. Cygnus X-1 also plays a role in the larger galactic ecosystem. Its powerful gravity, combined with the intense radiation from its accretion disk, can influence the composition and movement of interstellar gas over vast distances. This interaction contributes to the complex dynamics of star formation and galactic evolution in its corner of the Milky Way. Cygnus X-1, a powerful X-ray source in our galaxy, plays a significant role in shaping the energy dynamics of its surrounding cosmic environment. As a binary system consisting of a blue supergiant star and a black hole, it releases enormous amounts of energy through various processes. The black hole in Cygnus X-1 continuously pulls matter from its companion star, creating an accretion disk of superheated gas. This process generates intense X-ray emissions and powerful jets of particles that extend far into space. These jets, traveling at nearly the speed of light, inject energy and matter into the interstellar medium, influencing the composition and behavior of nearby gas clouds. The energy output from Cygnus X-1 affects the ionization state of surrounding gases, potentially triggering or suppressing star formation in its vicinity. This interaction creates a complex feedback loop where the black hole's activity influences the availability of material for future star formation, which in turn affects the long-term evolution of the galactic region. Moreover, the gravitational influence of Cygnus X-1 contributes to the overall dynamics of its galactic neighborhood. Its presence affects the motion of nearby stars and gas, potentially leading to the compression or dispersion of molecular clouds. This gravitational impact, combined with its energetic output, makes Cygnus X-1 a key player in the ongoing cosmic dance of energy and matter in its corner of the Milky Way. Cygnus X-1, a stellar mass black hole in our Milky Way galaxy, represents a class of objects that play crucial roles in galactic evolution. These compact, extremely dense remnants of massive stars exert significant influence on their surroundings through various mechanisms. Black holes like Cygnus X-1 act as cosmic recyclers, pulling in nearby gas and dust and ejecting a portion of this material in powerful jets. This process redistributes matter and energy throughout the galaxy, influencing star formation and the composition of interstellar gas. The intense radiation from the material falling into these black holes can ionize surrounding gas, affecting its ability to collapse and form new stars. Furthermore, the gravitational effects of black holes contribute to the overall dynamics of galaxies. As they orbit within a galaxy, they can disrupt star clusters and affect the motion of nearby stars. In some cases, this can lead to the scattering of stars from the galactic core to the outer regions, influencing the galaxy's structure and evolution over time. The study of objects like Cygnus X-1 also provides valuable insights into the life cycles of massive stars and the processes that shape galaxies. By observing how these black holes interact with their environments, scientists can better understand the complex interplay between different components of a galaxy and how they evolve together over cosmic timescales. Cygnus X-1, a powerful X-ray source in our galaxy, has a profound impact on its cosmic surroundings. This celestial object, believed to be a black hole, emits intense radiation that interacts with the surrounding space in various ways. The radiation from Cygnus X-1 primarily consists of high-energy X-rays and gamma rays. These energetic emissions ionize nearby gas clouds, stripping electrons from atoms and creating regions of hot, glowing plasma. This process can trigger the formation of new stars by compressing gas clouds, while simultaneously inhibiting star formation in other areas by dispersing molecular clouds. The powerful jets of particles ejected from Cygnus X-1 also play a crucial role in shaping its environment. These jets, traveling at nearly the speed of light, create massive shock waves as they collide with surrounding interstellar material. These collisions heat the nearby gas to extreme temperatures, causing it to emit radiation across various wavelengths of the electromagnetic spectrum. Furthermore, the radiation and particle jets from Cygnus X-1 contribute to the overall energy balance of the interstellar medium in its vicinity. This influx of energy influences the dynamics of nearby star systems and affects the chemical composition of the surrounding space by breaking apart molecules and creating new ionic species. The far-reaching effects of Cygnus X-1 demonstrate the significant influence that compact, high-energy objects can have on their cosmic neighborhoods. Cygnus X-1 provides astronomers with a unique laboratory for studying cosmic feedback mechanisms. As one of the brightest X-ray sources in our galaxy, this binary system consists of a blue supergiant star orbiting a black hole. The intense gravitational pull of the black hole draws material from its companion star, forming an accretion disk of superheated gas. This process of material transfer and accretion generates powerful jets of particles and energy, which shoot out from the black hole's poles at nearly the speed of light. These jets interact with the surrounding interstellar medium, creating shock waves and influencing the environment over vast distances. By observing these interactions, scientists can gain insights into how black holes regulate their own growth and affect the evolution of their host galaxies. The feedback mechanisms observed in Cygnus X-1 demonstrate the complex interplay between matter and energy in extreme cosmic environments. As the black hole consumes matter, it simultaneously expels a portion of it, effectively self-regulating its feeding process. This balance between inflow and outflow plays a crucial role in shaping the dynamics of galactic systems on much larger scales. Studying Cygnus X-1 allows researchers to better understand how these feedback processes operate in other, more distant systems. The knowledge gained from this nearby cosmic laboratory helps refine models of galaxy formation and evolution, shedding light on the intricate relationship between supermassive black holes and their host galaxies throughout the universe. Cygnus X-1, a powerful black hole in our galaxy, exerts a significant influence on its surrounding environment. This cosmic behemoth, with a mass about 15 times that of our Sun, creates intense gravitational forces that can both hinder and promote star formation in its vicinity. The strong gravitational pull of Cygnus X-1 can disrupt nearby gas clouds, preventing them from collapsing to form new stars. However, this disruption also creates shock waves and turbulence in the surrounding interstellar medium. These disturbances can compress other regions of gas and dust, potentially triggering the formation of new stars in areas farther from the black hole. Additionally, Cygnus X-1 emits powerful jets of radiation and particles that extend far into space. These jets interact with the surrounding gas, heating it and creating bubbles of hot plasma. The edges of these bubbles can become dense and cool, providing ideal conditions for new stars to form. The complex interplay between Cygnus X-1 and its environment demonstrates the dual nature of black holes in star formation. While they can inhibit star birth in their immediate vicinity, they also create conditions that may lead to increased star formation in surrounding regions, shaping the stellar population of their host galaxy. Cygnus X-1 plays a crucial role in our understanding of massive star evolution and the formation of black holes. As one of the first discovered black holes, this cosmic object has provided astronomers with valuable insights into the final stages of massive stars. The story of Cygnus X-1 begins with a massive star, likely over 40 times the mass of our Sun. When such enormous stars exhaust their nuclear fuel, they undergo a catastrophic collapse. In most cases, this results in a spectacular supernova explosion. However, Cygnus X-1 challenges this conventional wisdom, suggesting that some extremely massive stars might bypass the supernova stage entirely. Instead of exploding, the progenitor star of Cygnus X-1 appears to have collapsed directly into a black hole. This process, known as direct collapse, occurs when the star's core is so massive that not even the outward pressure of a supernova can overcome the inward pull of gravity. The existence of Cygnus X-1 thus demonstrates that the evolution of the most massive stars in our universe can take unexpected paths. Furthermore, Cygnus X-1 has helped scientists refine their models of stellar mass limits. By studying this system, researchers have gained a better understanding of just how massive a star needs to be to form a black hole rather than a neutron star. This knowledge is crucial for predicting the ultimate fate of other massive stars throughout the cosmos, shedding light on the processes that shape the evolution of galaxies. Cygnus X-1 offers us a fascinating glimpse into the ultimate fate of massive stars. This celestial object, located roughly 6,000 light-years from Earth, is one of the most studied systems in our galaxy. It consists of a blue supergiant star orbiting an invisible companion, which scientists have identified as a stellar mass black hole. The presence of this black hole in Cygnus X-1 provides crucial information about stellar evolution. It demonstrates that when extremely massive stars exhaust their nuclear fuel, they can collapse under their own gravity to form black holes. This process is far more dramatic than the fate awaiting smaller stars like our Sun, which will eventually become white dwarfs. Observations of Cygnus X-1 have allowed astronomers to study the behavior of matter around black holes. As material from the blue supergiant is pulled towards the black hole, it forms an accretion disk. This disk becomes incredibly hot due to friction and compression, emitting powerful X-rays that we can detect from Earth. These emissions help scientists understand the extreme physics at play in such environments. Furthermore, Cygnus X-1 serves as a testament to the accuracy of Einstein's theory of general relativity. The system's properties, including the orbital period of the two objects and the intense gravitational effects observed, align closely with predictions made by this fundamental theory of gravity. Thus, Cygnus X-1 not only illuminates the end stages of stellar life, but also provides a cosmic laboratory for testing our most advanced physical theories. Cygnus X-1 stands as a cosmic anomaly that has forced astronomers to rethink their understanding of stellar evolution and collapse. This extraordinary system consists of a blue supergiant star orbiting an incredibly dense, invisible companion. The invisible object's immense gravitational pull and its effects on surrounding matter strongly suggest it is a black hole. What makes Cygnus X-1 particularly intriguing is its mass. Most black holes form when massive stars exhaust their fuel and collapse under their own gravity. However, the black hole in Cygnus X-1 is estimated to be about 15 times the mass of our Sun. This is significantly more massive than what traditional models predicted for stellar collapse. The existence of such a massive black hole challenges our theories about how stars die. It suggests that some stars might collapse directly into black holes without first exploding as supernovae, a process astronomers call failed supernovae. This possibility forces us to reconsider the final stages of stellar evolution for the most massive stars in the universe. Furthermore, Cygnus X-1 has led scientists to explore new ideas about black hole formation, including the potential role of rapid rotation or reduced metal content in massive stars. These factors might allow for the creation of more massive black holes than previously thought possible through stellar collapse. Cygnus X-1 offers crucial insights into the relationship between star mass and black hole formation. This famous binary system consists of a blue supergiant star orbiting a black hole, providing astronomers with a unique opportunity to study black hole physics and stellar evolution. The black hole in Cygnus X-1 formed from a massive star that collapsed under its own gravity. By studying this system, scientists have determined that stars with initial masses greater than about 20 to 25 times that of our Sun are likely to end their lives as black holes. This finding helps establish a threshold for black hole formation in stellar evolution. Furthermore, Cygnus X-1 has allowed researchers to refine models of stellar mass loss during the late stages of a star's life. The black hole's mass, estimated to be around 15 times that of our Sun, suggests that its progenitor star lost a significant portion of its mass before collapse. This information is vital for understanding how massive stars evolve and how their final masses relate to the masses of the black holes they form. The study of Cygnus X-1 also provides clues about the role of metallicity in black hole formation. The system's composition suggests that even stars with relatively high metal content can form black holes, challenging earlier theories that only low metallicity stars could produce these exotic objects. Cygnus X-1 serves as a crucial laboratory for understanding the life cycle of massive stars and the formation of black holes. As one of the closest known black holes to Earth, it provides astronomers with an unparalleled opportunity to study these enigmatic objects in detail. By observing Cygnus X-1, scientists can gain insights into the processes that occur during the final stages of a massive star's life. This information helps refine models of stellar evolution, particularly for stars many times more massive than our Sun. These models, in turn, allow astronomers to make more accurate predictions about the fate of other massive stars throughout the universe. The study of Cygnus X-1 also sheds light on the mechanisms of black hole formation. By analyzing the properties of this system, including the mass of the black hole and its companion star, researchers can better understand the conditions necessary for a massive star to collapse into a black hole rather than exploding as a supernova. Furthermore, observations of Cygnus X-1 provide valuable data on the behavior of matter in extreme gravitational environments. This knowledge not only enhances our understanding of black holes, but also contributes to broader theories in astrophysics, potentially helping predict the ultimate fate of massive stars and the galaxies they inhabit. Cygnus X-1, a well-known black hole in our galaxy, offers valuable insights into the chemical enrichment of the universe through stellar evolution. This celestial object, once a massive star, has undergone the full cycle of stellar life and death, leaving behind a black hole and enriching its surroundings with heavy elements. The progenitor star of Cygnus X-1 was likely more than 40 times the mass of our Sun. During its lifetime, it fused lighter elements into heavier ones in its core, creating elements like carbon, oxygen, and even iron. When this star reached the end of its life, it exploded as a supernova, dispersing these newly formed heavy elements into space. This process of stellar nucleosynthesis and subsequent dispersal is crucial for the chemical evolution of the universe. The heavy elements produced by massive stars, like the progenitor of Cygnus X-1, become the building blocks for future generations of stars, planets, and even life itself. By studying the composition of the material around Cygnus X-1, scientists can better understand the types and quantities of elements produced by massive stars. Furthermore, the existence of Cygnus X-1 as a black hole provides evidence for the final stages of evolution for the most massive stars in the universe. This helps astronomers piece together the cosmic puzzle of how the universe became enriched with elements heavier than hydrogen and helium over time, shaping the diverse and complex cosmos we observe today. The companion star of Cygnus X-1 plays a crucial role in our understanding of binary star evolution, offering a unique window into the life cycles of massive stars and the formation of black holes. This blue supergiant, known as HDE 226868, orbits the black hole in a cosmic dance that has captivated astronomers for decades. By studying this companion star, scientists have gained valuable insights into the complex interactions between massive stars in binary systems. The star continuously loses mass to its black hole partner through stellar winds and gravitational pull, a process that significantly impacts the evolution of both objects. This mass transfer not only feeds the black hole, but also alters the course of the companion star's life, potentially hastening its own demise. The Cygnus X-1 system serves as a living laboratory for testing theories of stellar evolution in extreme environments. Observations of the companion star's properties, such as its temperature, size, and composition, help astronomers refine models of how massive stars age and interact in binary systems. These findings have broad implications, shedding light on the formation of other exotic objects like neutron stars and the processes that lead to supernova explosions. Furthermore, the existence of this binary system challenges our understanding of stellar lifespans and black hole formation. The companion star's presence and characteristics provide crucial data for calculating the age and history of the Cygnus X-1 system, offering clues about the conditions necessary for black holes to form and evolve in binary star systems throughout the universe. Cygnus X-1 presents some of the most extreme conditions known in the universe. This cosmic object is a binary system consisting of a blue supergiant star orbiting a black hole. The black hole, with a mass about 15 times that of our Sun, creates an incredibly strong gravitational field that warps the fabric of space-time around it. Near the black hole's event horizon, gravity becomes so intense that nothing, not even light, can escape its pull. This creates a region where the laws of physics, as we understand them, begin to break down. The extreme gravitational forces also cause time dilation, meaning time moves more slowly near the black hole compared to regions farther away. The black hole's powerful gravity pulls material from its companion star, forming an accretion disk of superheated gas and dust. This disk reaches temperatures of millions of degrees, far hotter than the surface of our Sun. As matter in the disk spirals towards the black hole, it accelerates to nearly the speed of light, releasing enormous amounts of energy in the form of X-rays and other high-energy radiation. These extreme conditions make Cygnus X-1 a natural laboratory for studying the behavior of matter and energy under circumstances impossible to replicate on Earth. Scientists use observations of this system to test theories of general relativity and to better understand the physics of black holes and their effects on surrounding space. Cygnus X-1 offers astronomers a unique laboratory for studying matter in extreme gravitational environments. This powerful X-ray source, located about 6,000 light-years from Earth, is a binary system consisting of a blue supergiant star and what scientists believe to be a black hole. The immense gravitational pull of the black hole draws material from its companion star, creating an accretion disk of superheated gas swirling around the black hole at incredible speeds. As this material plunges towards the black hole, it becomes compressed and heated to millions of degrees, emitting intense X-rays that we can detect from Earth. These X-rays provide valuable information about the behavior of matter in the presence of extremely strong gravitational fields, allowing scientists to test theories of general relativity and quantum mechanics in ways that would be impossible in Earth-based laboratories. By studying the patterns and variations in the X-ray emissions from Cygnus X-1, researchers can infer details about the structure of the accretion disk, the properties of the black hole, and the complex interactions between the two. This includes investigating phenomena such as frame dragging, where the rotation of the black hole distorts the fabric of space-time itself, and the behavior of matter at the event horizon, the point of no return beyond which nothing can escape the black hole's gravitational pull. Furthermore, Cygnus X-1 enables scientists to explore the limits of our understanding of physics in extreme conditions. The observations made of this system continue to challenge and refine our models of how matter behaves in the most extreme environments in the universe, pushing the boundaries of our knowledge and inspiring new questions about the nature of space, time, and gravity. Cygnus X-1, a binary star system containing a black hole, serves as a cosmic laboratory for studying plasma behavior under extreme conditions. This system showcases the intense interactions between a black hole and its companion star, offering valuable insights into high-energy astrophysics. The accretion disk surrounding the black hole in Cygnus X-1 is composed of superheated plasma, reaching temperatures of millions of degrees. As this plasma spirals towards the black hole, it experiences immense gravitational forces and extreme magnetic fields. These conditions cause the plasma to emit powerful X-rays, which we can observe and analyze from Earth. By studying the X-ray emissions from Cygnus X-1, scientists can better understand how plasma behaves in the presence of strong gravity and intense magnetic fields. This knowledge has applications beyond astrophysics, influencing research in fusion energy and plasma physics on Earth. The extreme environment around the black hole also provides a unique opportunity to test theories of general relativity and quantum mechanics. Furthermore, Cygnus X-1 exhibits powerful jets of plasma that are ejected from the vicinity of the black hole at nearly the speed of light. These jets offer insights into how energy can be extracted from rotating black holes and how plasma can be accelerated to relativistic speeds. By observing these phenomena, researchers can refine models of plasma behavior in other extreme astrophysical environments, such as active galactic nuclei and gamma-ray bursts. Cygnus X-1, a stellar mass black hole in our galaxy, acts as a cosmic particle accelerator on an enormous scale. This celestial powerhouse creates conditions that propel particles to extreme energies, rivaling and even surpassing the capabilities of our most advanced human-made accelerators. The process begins with the intense gravitational field of the black hole. As matter from its companion star spirals inward, it forms an accretion disk that heats up to millions of degrees. This superheated plasma becomes a breeding ground for high-energy particles. The black hole's rotation, combined with its powerful magnetic fields, creates a natural accelerator mechanism. Particles caught in this cosmic maelstrom are whipped around at incredible speeds, gaining energy with each revolution. Some of these particles are then ejected in powerful jets that extend for light years into space. These jets act as nature's version of a particle beam, hurling matter at velocities approaching the speed of light. The energies achieved in this natural accelerator far exceed what we can produce on Earth. Particles accelerated by Cygnus X-1 can reach energies millions of times higher than those in the Large Hadron Collider. This makes Cygnus X-1 an invaluable cosmic laboratory, allowing scientists to study particle physics in extreme conditions that are impossible to replicate on our planet. Cygnus X-1 provides astronomers with a unique laboratory for studying extreme physics. This binary star system contains a blue supergiant star orbiting what is believed to be a stellar mass black hole. By observing the intense X-ray emissions from Cygnus X-1, scientists can probe the behavior of matter in extraordinarily strong gravitational fields. The black hole in this system is constantly pulling material from its companion star, forming an accretion disk of superheated gas. As this material spirals inward, it reaches incredibly high speeds and temperatures, emitting powerful X-rays that we can detect from Earth. These observations allow researchers to test theories about how matter behaves near the event horizon of a black hole, where the laws of physics are pushed to their limits. Cygnus X-1 also offers insights into relativistic jets, powerful streams of particles ejected from the poles of some black holes at nearly the speed of light. By studying these jets, scientists can better understand the mechanisms that accelerate particles to such extreme velocities and the role these outflows play in shaping the surrounding space. Furthermore, the regular variations in X-ray emissions from Cygnus X-1 provide clues about the structure and dynamics of accretion disks, helping refine models of how black holes grow and interact with their environments. This knowledge not only applies to stellar mass black holes, but also informs our understanding of the supermassive black holes at the centers of galaxies. Cygnus X-1 serves as a cosmic laboratory that unites the realms of astrophysics and particle physics in remarkable ways. This binary star system, consisting of a blue supergiant star and a black hole, offers scientists a unique opportunity to study extreme physics in action. The intense gravitational pull of the black hole in Cygnus X-1 creates conditions that are impossible to replicate on Earth. As matter from the companion star falls towards the black hole, it forms an accretion disk that heats up to millions of degrees. This extreme environment allows researchers to observe how particles behave under intense gravitational fields and high-energy conditions. These observations provide valuable insights into fundamental physics theories, including general relativity and quantum mechanics. By studying the X-ray emissions from Cygnus X-1, scientists can test predictions about how matter behaves near the event horizon of a black hole, bridging the gap between the physics of the very large and the very small. Furthermore, the jets of particles ejected from the vicinity of the black hole in Cygnus X-1 offer clues about particle acceleration mechanisms. This knowledge not only enhances our understanding of black holes, but also informs research in particle physics, potentially shedding light on phenomena observed in particle accelerators on Earth. Cygnus X-1, while an invaluable source for studying black holes, presents several challenges as a laboratory for extreme physics. Its distance from Earth, approximately 6,000 light-years, makes detailed observations difficult. This vast separation limits our ability to capture high-resolution data, potentially obscuring subtle phenomena occurring near the event horizon. The dynamic nature of the Cygnus X-1 system also poses complications. Its companion star constantly feeds material into the black hole, creating a complex and ever-changing environment. This constant flux makes it challenging to isolate specific effects or conduct controlled experiments, as conditions never remain stable for long. Furthermore, the intense radiation emitted by the accretion disk surrounding the black hole can interfere with observations. This powerful emission can overwhelm more subtle signals, making it difficult to detect certain phenomena or gather precise measurements of the black hole's properties. Lastly, our current technology, while advanced, still struggles to probe the most extreme regions near the black hole. The intense gravitational fields and high-energy processes occurring there push the limits of our observational capabilities, leaving some of the most intriguing questions about black hole physics just beyond our reach. Cygnus X-1, the first black hole ever discovered, continues to intrigue astronomers and astrophysicists with several unanswered questions. One of the primary mysteries surrounds the exact mass of the black hole. While scientists have made estimates, Pinpointing its precise mass remains challenging due to the complex interactions with its companion star. Another area of ongoing research is the behavior of the accretion disk surrounding Cygnus X-1. Scientists are still working to fully understand the mechanisms that drive the powerful jets of material ejected from the black hole's vicinity. These jets, which shoot out at nearly the speed of light, raise questions about the extreme physics at play in such high-energy environments. The evolution of the Cygnus X-1 system also presents puzzles. Researchers are keen to unravel how this binary system formed and how it will change over time. Understanding its past and future could provide valuable insights into the life cycles of massive stars and the formation of black holes throughout the universe. Lastly, the impact of Cygnus X-1 on its surrounding space continues to be a subject of study. Scientists are investigating how the intense gravitational pull and radiation from the black hole affect nearby gas and dust, potentially influencing star formation in its cosmic neighborhood. These questions drive ongoing observations and theoretical work, making Cygnus X-1 a captivating subject in the field of astrophysics. Future space missions to study Cygnus X-1 could significantly expand our knowledge of black holes and their behavior. Advanced telescopes and instruments might allow scientists to observe Cygnus X-1 with unprecedented detail, potentially revealing new insights into the complex interactions between the black hole and its companion star. One key area of focus could be the accretion disk surrounding the black hole. By studying the disk with higher resolution and across a broader range of wavelengths, researchers might gain a better understanding of how matter behaves in extreme gravitational environments. This could shed light on the processes that drive the powerful jets of material ejected from the vicinity of the black hole. Future missions might also aim to measure the black hole's spin more accurately. This property is crucial for understanding the black hole's evolution and its effects on nearby spacetime. Improved measurements could help refine our models of black hole formation and growth throughout the universe. Additionally, long-term observations of Cygnus X-1 could reveal variations in its behavior over time, potentially uncovering new phenomena or patterns that are currently unknown. These discoveries could have far-reaching implications for our understanding of black holes and the extreme physics that govern them. To enhance our study of Cygnus X-1, several technological advancements are crucial. Improved X-ray telescopes with higher sensitivity and resolution would allow us to observe the black hole's accretion disk in greater detail, revealing more about its structure and behavior. These advanced instruments could help us better understand the extreme physics at play near the event horizon. Gravitational wave detectors with increased sensitivity would be invaluable for studying Cygnus X-1. By detecting gravitational waves from this system, we could gain new insights into the black hole's properties and its interactions with its companion star. This would require both space-based and ground-based detectors working in tandem to capture a wide range of frequencies. Advanced radio telescopes and interferometry networks could provide sharper images of the jet emissions from Cygnus X-1. This would allow us to study the mechanisms behind jet formation and propagation in greater detail, shedding light on how black holes influence their surrounding environment. Lastly, more powerful supercomputers and sophisticated modeling software are needed to simulate the complex interactions within the Cygnus X-1 system. These simulations could help us interpret observational data more accurately and test theoretical predictions about black hole behavior in extreme conditions. Machine learning and artificial intelligence are revolutionizing our approach to studying black holes like Cygnus X-1. These advanced computational techniques can sift through vast amounts of observational data, detecting patterns and anomalies that might elude human researchers. For Cygnus X-1 specifically, AI algorithms could analyze the complex X-ray emissions from the accretion disk surrounding the black hole. These emissions fluctuate rapidly, and machine learning models could identify subtle changes that might indicate new phenomena or confirm theoretical predictions about black hole behavior. Artificial intelligence could also improve our understanding of the companion star in the Cygnus X-1 system. By processing spectroscopic data, AI might reveal intricate details about the star's composition and how it's affected by its massive black hole neighbor. This could provide insights into stellar evolution in extreme environments. Furthermore, machine learning could enhance our ability to model the complex gravitational interactions within the Cygnus X-1 system. By simulating millions of possible scenarios and comparing them to observational data, AI could help refine our models of black hole physics and potentially uncover new aspects of general relativity in action. Cygnus X-1, the first black hole ever discovered, continues to be a source of fascination and potential breakthroughs in astrophysics. Future observations of this cosmic giant could reveal crucial information about the nature of space-time itself. Scientists are particularly interested in studying the behavior of matter as it approaches the event horizon, the point of no return around a black hole. Advanced instruments might allow us to observe this process in unprecedented detail, potentially confirming or challenging our current theories about gravity and the fabric of space. Another exciting avenue of research involves the jets of particles that Cygnus X-1 emits. These powerful streams of matter, accelerated to nearly the speed of light, could hold clues about the mechanisms behind cosmic ray acceleration. Understanding this process could shed light on the most energetic phenomena in the universe and how they shape galactic evolution. The spin of Cygnus X-1 is also of great interest. Precise measurements of its rotation could provide insights into the formation and growth of black holes. If we can determine how fast Cygnus X-1 is spinning, we might be able to trace its history back to its origins, potentially revealing new information about the life cycles of massive stars and the processes that lead to black hole formation. Lastly, studying the interactions between Cygnus X-1 and its companion star could improve our understanding of binary star systems and their evolution. This could have far-reaching implications for our models of stellar populations and galactic structure, ultimately refining our view of the cosmic landscape. Cygnus X-1 stands as a remarkable beacon in our quest to understand black holes. As one of the closest known black holes to Earth, it provides astronomers with an unparalleled opportunity to study these enigmatic cosmic objects in detail. The wealth of data gathered from Cygnus X-1 has helped refine our models of black hole behavior and their interactions with companion stars. By closely examining Cygnus X-1, scientists have gained crucial insights into the process of mass transfer between a black hole and its stellar companion. This knowledge is invaluable when searching for other black holes that might be lurking in binary systems throughout our galaxy. The distinctive X-ray emissions and gravitational effects observed in Cygnus X-1 serve as a template, guiding astronomers in their hunt for similar systems. Furthermore, the study of Cygnus X-1 has led to advancements in our understanding of accretion disks, the swirling rings of matter that surround black holes. These disks play a crucial role in the growth and evolution of black holes, and the lessons learned from Cygnus X-1 can be applied to the search for and study of other black hole systems, including those that might be significantly different in size or environment. The techniques and technologies developed to observe and analyze Cygnus X-1 are also proving invaluable in the broader search for black holes. From improved X-ray detection methods to more sophisticated data analysis algorithms, these tools are enhancing our ability to identify and study black holes across the cosmos, potentially leading to the discovery of even more unique and exotic specimens in the vast expanse of space. Cygnus X-1, a stellar mass black hole in our galaxy, serves as a cosmic laboratory for testing theories of gravity and spacetime. This remarkable object, first discovered in 1964, continues to push the boundaries of our understanding of extreme gravitational environments. As one of the closest known black holes to Earth, Cygnus X-1 offers astronomers a unique opportunity to study the behavior of matter and energy in the presence of intense gravitational fields. Its proximity allows for detailed observations that can help refine or challenge our current models of gravity, particularly Einstein's theory of general relativity. Future observations of Cygnus X-1 will likely focus on the precise measurements of the black hole's properties, such as its mass, spin, and the structure of its accretion disk. Advanced telescopes and improved data analysis techniques may reveal subtle deviations from the predictions of general relativity, potentially pointing towards new theories of gravity or modifications to our current understanding of spacetime. Additionally, Cygnus X-1 could play a crucial role in testing theories that attempt to reconcile general relativity with quantum mechanics, such as string theory or loop quantum gravity. By providing a real-world testbed for these advanced concepts, this stellar black hole may help unlock the secrets of quantum gravity and bring us closer to a unified theory of the universe. Cygnus X-1 has captured the imagination of science fiction creators since its discovery in 1964. This powerful X-ray source, now confirmed to be a black hole, has appeared in various forms across literature, television, and music. In literature, Cygnus X-1 often serves as a backdrop for stories exploring the extremes of space and time. Authors have used it as a gateway to other dimensions or as a source of immense energy that advanced civilizations might harness. Some narratives depict daring missions to study the black hole up close, pushing the boundaries of human exploration and scientific understanding. Television and film have also embraced Cygnus X-1 as a dramatic setting. Science fiction shows frequently portray it as a dangerous anomaly that threatens passing starships or as a mysterious phenomenon holding secrets about the nature of the universe. Visual media allows creators to imagine the spectacular accretion disk and intense gravitational effects around the black hole, bringing these cosmic wonders to life for viewers. Perhaps most famously in popular culture, the rock band Rush created a two-part epic song titled Cygnus X-1 that tells the story of an intrepid explorer venturing into the black hole. This musical journey, blending scientific concepts with poetic license, has introduced many fans to the real-world astronomical object and sparked further interest in black hole physics. Cygnus X-1 has played a pivotal role in shaping public understanding of black holes, serving as a crucial bridge between theoretical predictions and observable evidence. Discovered in 1964 during a rocket flight, this cosmic object initially puzzled astronomers with its intense X-ray emissions. As scientists studied it further, they realized they were witnessing something extraordinary, the first strong candidate for a black hole in our galaxy. The identification of Cygnus X-1 as a likely black hole captured the public imagination, transforming these enigmatic objects from mathematical curiosities into tangible celestial entities. It provided a focal point for discussions about the nature of space, time, and gravity, helping to bring complex astrophysical concepts into mainstream conversation. The object's ongoing study has continually refined our understanding of how black holes interact with their surroundings, particularly in binary systems. Moreover, Cygnus X-1 has become a touchstone for explaining black hole behavior to the public. Its dramatic interactions with its companion star, including the visible accretion disk and powerful jets, offer vivid illustrations of black hole physics. These features have been widely used in educational materials, documentaries, and popular science books to help visualize the otherwise invisible properties of black holes. The legacy of Cygnus X-1 extends beyond its scientific importance. It has inspired countless discussions about the nature of the universe, the limits of human knowledge, and our place in the cosmos. By providing concrete evidence for these extreme cosmic objects, Cygnus X-1 has helped to demystify black holes, transforming them from science fiction fantasies into subjects of serious scientific inquiry and public fascination. Artists have found inspiration in Cygnus X-1, interpreting this enigmatic cosmic object through various mediums. Painters have created striking visual representations, often depicting the black hole as a dark vortex against a backdrop of swirling gases and distant stars. These artworks frequently emphasize the intense gravitational pull of the black hole, showing matter being drawn into its maw in vibrant streaks of color. Sculptors have also tackled the challenge of representing Cygnus X-1 in 3 dimensions. Some have crafted abstract pieces that capture the essence of a black hole's immense gravity, using materials like polished metal or dark stone to convey its power and mystery. Others have created more literal interpretations, with intricate models showing the black hole's accretion disk and its companion star. Digital artists have leveraged advanced computer graphics to produce detailed visualizations of Cygnus X-1. These often incorporate scientific data to create accurate representations of the black hole's environment, including its powerful jets of plasma and the distorted space-time around it. Such digital artworks have been invaluable in helping scientists communicate complex concepts to the public. Musicians have also drawn inspiration from Cygnus X-1, composing pieces that attempt to capture its cosmic drama through sound. These compositions often feature deep, resonant tones to represent the black hole itself, accompanied by swirling melodies that evoke the turbulent space around it. Some artists have even incorporated actual radio emissions from the Cygnus region into their music, creating a direct link between the artwork and its celestial muse. Cygnus X-1, the first strong black hole candidate ever discovered, has been the subject of several misconceptions in popular culture. One common misunderstanding is that Cygnus X-1 is a single, isolated object. In reality, it is a binary system consisting of a blue supergiant star and a black hole orbiting each other. Another widespread misconception is that Cygnus X-1 poses an immediate threat to Earth or nearby star systems. While it is a powerful source of X-rays and other high-energy radiation, its effects are limited to its immediate vicinity and do not pose any danger to our planet. Some people mistakenly believe that Cygnus X-1 is visible to the naked eye. Although the system is located in the constellation Cygnus, which is visible from Earth, the black hole itself cannot be directly observed without specialized equipment. What we see is the effect of the black hole on its companion star and the surrounding space. Lastly, there is a misconception that Cygnus X-1 is unique in the universe. While it was the first strong black hole candidate identified, astronomers have since discovered numerous other black hole binary systems throughout our galaxy and beyond. Cygnus X-1, the first black hole ever discovered, has captivated not only scientists but also musicians and songwriters. Its mysterious nature and cosmic significance have sparked creative inspiration across various genres of music. One of the most famous musical tributes to Cygnus X-1 comes from the Canadian progressive rock band Rush. They dedicated 2 epic songs to this celestial object: Cygnus X-1 Book 1, The Voyage, and Cygnus X-1 Book 2, Hemispheres. These compositions blend intricate instrumentals with lyrics that explore themes of space exploration, human curiosity, and the unknown. Other musicians have also drawn inspiration from Cygnus X-1. Electronic and ambient artists often incorporate the concept of black holes, including Cygnus X-1, into their work, creating soundscapes that evoke the vastness and mystery of space. Some heavy metal bands have used the power and intensity associated with black holes as metaphors in their lyrics, referencing Cygnus X-1 as a symbol of unstoppable force or cosmic destruction. The allure of Cygnus X-1 in music demonstrates how scientific discoveries can transcend their original context and influence culture. It serves as a bridge between the worlds of science and art, inspiring creative minds to explore the wonders of the universe through sound and lyrics. Cygnus X-1 serves as a powerful tool for science education and outreach, captivating both students and the general public with its intriguing properties. As one of the most studied celestial objects, This binary system offers a unique opportunity to explore complex astrophysical concepts in a tangible way. The story of Cygnus X-1 begins with its discovery in 1964 during a rocket flight, when it became the first cosmic X-ray source widely accepted to be a black hole. This historical significance makes it an excellent starting point for discussions about the evolution of our understanding of the universe and the nature of black holes. Scientists and educators often use Cygnus X-1 to explain phenomena such as accretion disks, X-ray emissions, and the behavior of matter near extremely dense objects. Its binary nature, consisting of a black hole and a blue supergiant star, provides a real-world example of how these massive cosmic entities interact with their surroundings, making abstract concepts more concrete for learners. Furthermore, Cygnus X-1 continues to be at the forefront of astrophysical research, allowing educators to demonstrate how ongoing scientific investigations shape our knowledge. By showcasing the methods used to study this system, including X-ray astronomy and gravitational wave detection, it inspires future generations of scientists and illustrates the dynamic nature of scientific discovery. The discovery of Cygnus X-1 has become a fascinating tale in the annals of astrophysics, capturing the imagination of scientists and the public alike. This cosmic drama began in the 1960s when astronomers detected an unusually strong source of X-rays in the constellation Cygnus. Unlike other known X-ray sources, this one defied easy explanation. As scientists investigated further, they realized they might be observing something extraordinary, the first potential black hole ever detected. This realization sparked intense debate and research. The story gained additional intrigue when it became the subject of a famous scientific wager between physicists Stephen Hawking and Kip Thorne. Hawking bet against the object being a black hole, while Thorne was convinced it was. This high-stakes scientific gamble added a human element to the cosmic mystery. The saga of Cygnus X-1 has been featured in numerous documentaries, popular science books, and even inspired artistic works. It has become a prime example of how scientific discovery unfolds, showcasing the process of observation, hypothesis, and debate that drives our understanding of the universe forward. The ongoing study of Cygnus X-1 continues to yield new insights, with recent observations refining our understanding of its mass and spin. This evolving story demonstrates how our knowledge of the cosmos is constantly expanding, making Cygnus X-1 an enduring icon in the field of astrophysics. Cygnus X-1 and Sagittarius A star are both black holes, but they differ significantly in size, location, and formation. Cygnus X-1 is a stellar mass black hole formed from the collapse of a massive star. It sits roughly 6,000 light-years from Earth in the constellation Cygnus. This cosmic behemoth weighs about 15 times the mass of our Sun, making it one of the most massive stellar black holes known. In contrast, Sagittarius A star is a supermassive black hole lurking at the heart of our Milky Way galaxy, approximately 26,000 light-years from Earth. It dwarfs Cygnus X-1 with a mass of about 4 million suns. This enormous mass is packed into a surprisingly small space, smaller than our solar system. While Cygnus X-1 actively feeds on material from a companion star, creating spectacular X-ray emissions, Sagittarius A star is relatively quiet. It occasionally flares up when it consumes nearby gas and dust, but generally maintains a low profile despite its immense gravitational influence on surrounding stars. The study of these two black holes offers astronomers valuable insights into different stages of black hole evolution and behavior. Cygnus X-1 represents the end state of massive stars, while Sagittarius A star exemplifies the giants that shape entire galaxies. Their contrasts highlight the diverse nature of these cosmic enigmas, from stellar remnants to galactic titans. Cygnus X-1 shares many fundamental characteristics with other stellar mass black holes found in binary systems throughout our galaxy. Like its counterparts, Cygnus X-1 formed from the collapse of a massive star, creating an incredibly dense object with a gravitational pull so strong that not even light can escape its grasp. This powerful gravity allows Cygnus X-1 to draw material from its companion star, forming an accretion disk that emits intense X-rays as matter spirals inward. However, Cygnus X-1 stands out in several ways. It is one of the closest known black holes to Earth, located approximately 6,000 light-years away, making it an invaluable subject for astronomical study. The black hole in Cygnus X-1 is also notably massive, with estimates suggesting it contains about 15 times the mass of our Sun. This places it at the upper end of the mass range for stellar mass black holes. Another distinguishing feature of Cygnus X-1 is its companion star. Unlike many black holes in binary systems that pair with smaller, less massive stars, Cygnus X-1 orbits a blue supergiant. This massive, hot star provides a substantial source of material for the black hole to consume, contributing to its status as one of the brightest X-ray sources in our sky. The unique properties of Cygnus X-1 have made it a crucial target for astronomers seeking to understand the physics of black holes and their interactions with companion stars. Its study continues to provide valuable insights into the life cycles of massive stars and the extreme environments created by these cosmic giants. Cygnus X-1 is a stellar mass black hole, fundamentally different from the supermassive behemoths lurking at the hearts of galaxies. While both are cosmic vacuum cleaners, their origins and characteristics set them apart in significant ways. Formed from the collapse of a massive star, Cygnus X-1 is relatively small, with a mass about 15 times that of our Sun. This compact powerhouse is part of a binary system, locked in a gravitational dance with a blue supergiant star. As it siphons material from its companion, Cygnus X-1 creates a brilliant accretion disk, making it one of the brightest X-ray sources in our sky. Supermassive black holes, on the other hand, are true giants of the cosmos. With masses ranging from millions to billions of times that of the Sun, they dwarf their stellar mass cousins. These cosmic monsters reside at the centers of most large galaxies, including our own Milky Way. Their formation remains a subject of intense study, with theories suggesting they might have grown from smaller black holes, merging over time, or formed directly from the collapse of enormous gas clouds in the early universe. The influence of these two types of black holes also differs dramatically. While Cygnus X-1 affects its immediate stellar neighborhood, supermassive black holes shape the evolution and structure of entire galaxies. Their immense gravitational pull influences star formation and galactic dynamics on a grand scale, making them crucial players in the cosmic story of galactic evolution. Cygnus X-1 stands out as a crucial benchmark in our understanding of black holes. As one of the first discovered black holes, it continues to provide valuable insights when compared to other known black holes throughout the universe. The mass of Cygnus X-1, estimated at around 21 times that of our Sun, places it in the category of stellar mass black holes. This makes it an excellent subject for comparison with both smaller and larger black holes. By studying how Cygnus X-1 behaves in relation to its binary companion star, scientists can better understand the gravitational effects and accretion processes of black holes in general. Observations of Cygnus X-1 have revealed intense X-ray emissions, which are characteristic of matter falling into a black hole. By comparing these emissions to those of other black holes, researchers can refine models of how material behaves in the extreme gravitational environments near event horizons. This comparative analysis helps in developing a more comprehensive picture of black hole physics across different scales. Furthermore, the spin rate of Cygnus X-1, which is close to the theoretical maximum, provides a unique opportunity to test Einstein's theory of general relativity under extreme conditions. Comparing this rapidly spinning black hole to others with different spin rates allows scientists to explore how rotation affects the space-time fabric around black holes, advancing our knowledge of these enigmatic cosmic objects. Cygnus X-1 stands out among known black holes due to its unique and dynamic environment. This stellar mass black hole is locked in a cosmic dance with a massive blue supergiant star, creating a binary system that sets it apart from many of its counterparts. The intense gravitational pull of Cygnus X-1 strips material from its companion star, forming a swirling accretion disk of superheated gas. This process generates powerful X-ray emissions, making Cygnus X-1 one of the brightest X-ray sources in our galaxy. The interaction between the black hole and its stellar partner also produces relativistic jets, streams of particles ejected at nearly the speed of light. Unlike isolated black holes, the environment around Cygnus X-1 is constantly evolving. The stellar wind from the companion star interacts with the black hole's accretion disk, creating complex patterns of gas flow and radiation. This dynamic interplay offers astronomers a unique laboratory for studying black hole physics and the behavior of matter under extreme conditions. The proximity of Cygnus X-1 to Earth, compared to many other known black holes, allows for more detailed observations. This has enabled scientists to gather valuable data on phenomena such as frame dragging and the behavior of space-time near a black hole, contributing significantly to our understanding of these cosmic enigmas. Cygnus X-1 holds a special place in the realm of black holes, distinguished by several remarkable characteristics. As one of the first discovered black holes, it paved the way for our understanding of these cosmic enigmas. This celestial object is part of a binary system, locked in a cosmic dance with a blue supergiant star. Their gravitational tango creates an extraordinary spectacle, with the black hole drawing matter from its companion in a process called accretion. What truly sets Cygnus X-1 apart is its relatively close proximity to Earth, at a distance of about 6,000 light-years. This nearness allows astronomers to study it in unprecedented detail, making it a cosmic laboratory for testing theories of general relativity and black hole physics. The black hole itself is estimated to be around 15 times the mass of our Sun, classifying it as a stellar mass black hole. Another intriguing aspect of Cygnus X-1 is its rapid rotation. It spins at nearly half the speed of light, making it one of the fastest spinning black holes ever observed. This extreme rotation warps the spacetime around it in fascinating ways, providing valuable insights into the behavior of matter and energy in extreme gravitational environments. The intense X-ray emissions from Cygnus X-1 also make it a standout object. These emissions, produced as matter from the companion star falls into the black hole, fluctuate on timescales as short as milliseconds. This variability offers astronomers a unique window into the dynamic processes occurring near the event horizon, the point of no return around a black hole. Cygnus X-1 has played a pivotal role in shaping our understanding of black holes and their prevalence in the universe. As one of the first discovered black hole candidates, this cosmic object has served as a crucial laboratory for testing theories about these enigmatic celestial bodies. The intense study of Cygnus X-1 has provided strong evidence for the existence of stellar mass black holes, which form from the collapse of massive stars. By observing the behavior of the companion star orbiting the black hole, scientists have been able to estimate the mass of Cygnus X-1, confirming it is too dense to be anything other than a black hole. This discovery has led astronomers to search for similar systems throughout our galaxy and beyond, revealing that stellar mass black holes are far more common than once thought. The techniques developed to study Cygnus X-1 have been applied to other binary systems, allowing researchers to identify numerous black hole candidates and better understand their formation and evolution. Furthermore, the study of Cygnus X-1 has helped scientists refine models of how black holes interact with their surroundings, particularly in binary systems. This knowledge has been instrumental in predicting and identifying other black hole populations, including intermediate mass and supermassive black holes, expanding our view of the diverse black hole landscape across the cosmos. Cygnus X-1 has been a pivotal object in advancing our understanding of cosmic evolution, particularly in the realm of black holes and stellar life cycles. This binary star system, located about 6,000 light-years from Earth, consists of a blue supergiant star orbiting an invisible companion that scientists have identified as a black hole. The study of Cygnus X-1 has provided crucial insights into the formation and behavior of stellar mass black holes. By observing the interactions between the black hole and its companion star, researchers have gained valuable data on how matter behaves in extreme gravitational environments. This information helps us piece together the complex processes that occur at the end of a massive star's life, shedding light on the evolutionary path from stellar birth to cosmic recycling. Furthermore, Cygnus X-1 has been instrumental in validating aspects of Einstein's theory of general relativity. The system's intense gravitational fields and high-energy emissions serve as a natural laboratory for testing predictions about space-time curvature and the behavior of matter near black holes. These observations contribute to our broader understanding of how gravity shapes the universe on both stellar and galactic scales. The ongoing study of Cygnus X-1 continues to refine our models of stellar evolution, black hole physics, and the role these extreme objects play in shaping galactic structures. By examining systems like Cygnus X-1, scientists can better understand the cosmic recycling process, where the deaths of massive stars seed the universe with heavy elements essential for the formation of planets and, ultimately, life itself. Cygnus X-1, a powerful X-ray source in our galaxy, offers valuable insights into the early universe. This celestial object is a binary system consisting of a blue supergiant star orbiting a black hole, one of the first such systems ever discovered. By studying Cygnus X-1, astronomers have gained crucial information about the formation and evolution of black holes, which in turn sheds light on the conditions present in the early cosmos. The black hole in Cygnus X-1 is believed to have formed from the collapse of a massive star that existed when the universe was much younger. Its properties provide clues about the first generation of stars that emerged after the Big Bang. These early stars, far more massive than those we see today, likely produced the first black holes in the universe. Furthermore, the intense X-ray emissions from Cygnus X-1 allow scientists to study the behavior of matter in extreme gravitational fields. This knowledge helps refine our understanding of the physical laws that governed the early universe when densities and temperatures were far higher than they are now. Cygnus X-1 also serves as a laboratory for testing theories of general relativity in strong gravitational fields. These tests contribute to our comprehension of how gravity behaved in the infant universe, potentially offering clues about the nature of dark matter and dark energy, which played crucial roles in cosmic evolution from the earliest times. Objects like Cygnus X-1, which is a well-known black hole, play a significant role in shaping the large-scale structure of the universe. These massive cosmic entities exert tremendous gravitational influence on their surroundings, affecting the distribution of matter and energy across vast distances. Black holes like Cygnus X-1 are often found at the centers of galaxies, where they can grow to become supermassive black holes. As these objects consume nearby matter, they release enormous amounts of energy in the form of radiation and powerful jets. This energy output can heat up surrounding gas, preventing it from cooling and forming new stars. This process, known as feedback, helps regulate star formation in galaxies and influences their overall evolution. On an even larger scale, the gravitational pull of black holes contributes to the formation of galaxy clusters and superclusters. These massive structures are held together by the combined gravitational force of their constituent galaxies and the dark matter halos that surround them. Black holes, as some of the most massive objects in the universe, play a crucial role in this cosmic web of matter. Furthermore, the jets emitted by active black holes can extend far beyond their host galaxies, interacting with the intergalactic medium. This interaction can help distribute heavy elements throughout space and even trigger star formation in distant regions. In this way, objects like Cygnus X-1 contribute to the complex interplay of forces that shape the large-scale structure of the cosmos, influencing the distribution of matter and energy across billions of light-years. Black holes like Cygnus X-1 play a crucial role in shaping the life cycle and evolution of galaxies. These cosmic behemoths, formed from the remnants of massive stars, exert a profound influence on their surroundings through their immense gravitational pull and energy output. At the heart of most galaxies, including our Milky Way, lie supermassive black holes, millions or even billions of times more massive than Cygnus X-1. These central black holes act as cosmic regulators, influencing star formation and galactic structure. As matter falls into a black hole, it forms an accretion disk, heating up and emitting powerful jets of radiation and particles. This process can either trigger star formation by compressing nearby gas clouds or suppress it by blowing gas away from the galaxy. Black holes also play a role in galactic mergers. When two galaxies collide, their central black holes eventually merge, releasing enormous amounts of energy in the form of gravitational waves. This cosmic dance of black holes contributes to the overall structure and distribution of galaxies in the universe. Furthermore, black holes like Cygnus X-1 serve as cosmic laboratories, allowing scientists to study extreme physics and test theories of gravity. By observing how matter behaves near these objects, researchers gain insights into the fundamental nature of space, time, and the universe itself, deepening our understanding of galactic evolution and cosmic history. Cygnus X-1, a famous black hole in our galaxy, has played a crucial role in shaping our understanding of stellar evolution and extreme gravitational environments. However, its connection to dark matter and dark energy is less direct. The study of Cygnus X-1 has primarily contributed to our knowledge of black holes and the behavior of matter in intense gravitational fields. This research has helped refine our models of gravity, which in turn inform our understanding of dark matter's gravitational effects on galaxies and galaxy clusters. While Cygnus X-1 itself does not directly reveal information about dark matter or dark energy, the techniques developed to study it have been applied to observations of galactic rotation and cosmic structure. These observations have led to the inference of dark matter's existence and the discovery of dark energy's effects on cosmic expansion. Ultimately, Cygnus X-1 serves as a valuable testing ground for theories of gravity, providing a foundation for the complex models used to explain the behavior of dark matter and dark energy on cosmic scales. Its study continues to push the boundaries of our understanding of the universe's most extreme phenomena. Cygnus X-1, the first black hole ever discovered, continues to shape our understanding of the universe and even lend support to some multiverse theories. This stellar mass black hole, located in the constellation Cygnus, provides a unique laboratory for testing extreme physics and exploring the boundaries of our known universe. The existence of Cygnus X-1 and other black holes like it suggests that our universe has specific physical constants that allow for their formation. These constants, such as the strength of gravity and the speed of light, seem finely tuned to permit the evolution of stars, galaxies, and ultimately, life. This apparent fine-tuning has led some scientists to propose the multiverse theory, which posits that our universe is just one of many, each with its own set of physical laws. In the context of multiverse theories, Cygnus X-1 represents a universe where the conditions are just right for black holes to form. Other universes within the multiverse might have different physical constants, resulting in dramatically different cosmic structures or even the absence of black holes altogether. The study of Cygnus X-1 and similar objects helps scientists refine their models of black hole formation and behavior, potentially providing clues about the range of possible universes that could exist within a multiverse framework. Furthermore, some theories suggest that black holes like Cygnus X-1 could be gateways to other universes or dimensions. While this remains highly speculative, the extreme gravitational environment of black holes pushes the limits of our current understanding of physics, potentially opening doors to new realms of theoretical exploration that could support or challenge multiverse concepts. Cygnus X-1, a powerful X-ray source in our galaxy, offers valuable insights into the nature of black holes and the fundamental forces shaping our universe. As one of the first discovered black hole candidates, it serves as a cosmic laboratory for testing our understanding of extreme physics. By observing Cygnus X-1, scientists can study the behavior of matter and energy in the most intense gravitational fields known to exist. This information helps refine our models of how massive stars collapse and form black holes, a process that plays a crucial role in the life cycle of galaxies. Furthermore, the intense gravitational effects around Cygnus X-1 provide a unique opportunity to test Einstein's theory of general relativity under extreme conditions. These tests can reveal potential limitations or necessary modifications to our current understanding of gravity, which is essential for predicting the long-term evolution of the universe. The study of Cygnus X-1 and similar systems also contributes to our knowledge of how black holes influence their surroundings, including their role in regulating star formation and galactic evolution. This understanding is crucial for predicting how the universe will change over vast timescales, potentially offering clues about its ultimate fate, whether it will expand forever, collapse back on itself, or reach some other cosmic endpoint.